What if the world around you, the stars above, the ground beneath your feet, even the thoughts in your mind, aren't quite as solid or real as they seem? What if reality, as we know it, is just a fragile illusion, a fleeting mirage in the vast cosmic theater of space? These aren't just the musings of science fiction. They're questions that physicists, philosophers, and even astronauts grapple with when they peer into the profound mysteries of the universe. Today, we're diving deep into 50 mind-bending theories about the nature of reality itself. Theories that stretch the limits of human understanding and challenge everything we think we know about existence. Picture this: you're floating in the infinite blackness of space, untethered from Earth's gravity, and suddenly, the very fabric of reality feels different. Time bends, light behaves strangely, the rules you've always relied on start to unravel. This isn't just a thought experiment, it's a glimpse into the radical ideas that suggest our universe might be far weirder, far more mysterious than we've ever dared to imagine. From the Holographic Principle, which proposes that our three-dimensional world is nothing more than a two-dimensional projection, to simulations so advanced we'd never know we were living inside them, these theories don't just question reality, they shatter it. But here's the most thrilling part: every single one of these ideas is grounded in real science, in the observations and equations of some of the brightest minds humanity has ever known. This isn't fantasy, it's the cutting edge of our quest to understand the cosmos, and that's why we're here, to explore these 50 theories, each more astonishing than the last, and to ask together, what if we've only scratched the surface of what's truly out there? So settle in, open your mind, and let's embark on a journey that might just change the way you see everything. One of the most startling theories about the nature of reality suggests we might be living inside an elaborate simulation. A cosmic video game, if you will, designed by a civilization so advanced their technology is indistinguishable from what we'd call nature. Think about the games we play today, with hyper-realistic graphics and artificial intelligence so sophisticated, virtual characters believe their world is real. Now scale that up by billions of years. If a future civilization could create simulations indistinguishable from reality, what are the odds we're the original version? This idea isn't just sci-fi speculation. Philosopher Nick Bostrom laid out a compelling trilemma, arguing one of three things must be true. Either civilizations like ours never reach the technological level to create such simulations, they choose not to run them despite having the ability, or here's the unsettling part, we are almost certainly living inside one. The math is chilling. If even a fraction of advanced civilizations run ancestor simulations to study their history, the number of simulated minds would vastly outnumber real ones. Statistically, you're probably not the exception. The Fermi paradox, the eerie silence of the cosmos despite the high probability of alien life, might find an answer here. If reality is a simulation, the universe could be intentionally empty, rendering vast stretches of space as mere background code to save processing power. Even Elon Musk has weighed in, suggesting the odds we're in base reality are 1 in billions. But how would we know? Some physicists propose looking for pixelation in the fabric of space-time, tiny glitches in the cosmic code. Others suggest fundamental limits, like the speed of light, might just be processing constraints. Picture digital grids superimposed over nebulas and galaxies, a hidden framework humming beneath the surface of what we perceive. Whether the simulation hypothesis holds water or not, it forces us to confront a humbling possibility. Reality might be far stranger than we ever dreamed. But if we truly are living in a simulated reality, where are the telltale signs, the cracks in the code? Some researchers point to déjà vu as a potential glitch, that eerie sensation of reliving a moment you know you've never experienced. Could it be a hiccup in the system, a brief overlap of saved data, Others highlight quantum mechanics, where particles behave differently when observed, almost as if the simulation conserves processing power by only rendering details when someone's looking. Even the infamous double-slit experiment, where light acts as both a particle and a wave, feels less like a law of physics and more like a software shortcut. Then there's the Mandela effect, where large groups misremember events like the Berenstain Bears being spelled Berenstein or Nelson Mandela dying in prison. Skeptics dismiss it as faulty memory, but could these inconsistencies be patches in the simulation, updates rolled out with unintended side effects? Mathematicians have even searched for pixelation in the cosmic microwave background, the afterglow of the Big Bang, hunting for unnatural geometric patterns that might reveal the underlying code of the universe. But here's the real kicker: if we're simulations, do our choices even matter? Some argue morality collapses under this theory. Why care about consequences in a world that isn't real? Yet others counter that our experiences, simulated or not, feel undeniably vivid. Pain, joy, love, they're just as real to us. Maybe the question isn't whether we're in a simulation, but what we do with the awareness that reality might be far more malleable than we ever imagined. After all, if this is a game, shouldn't we play it with curiosity, kindness, and a relentless urge to uncover the rules? Now let's turn to something even more radical: the idea that our three-dimensional universe might just be a grand illusion, a cosmic sleight of hand. Enter the holographic principle, a theory emerging from the fiery crossroads of string theory and black hole physics. Picture a black hole's event horizon, that point of no return where gravity is so strong not even light can escape. When matter falls in, its information, the blueprint of what it was, doesn't just vanish. According to the laws of thermodynamics, it gets imprinted on the surface of the event horizon, like a projector screen at the edge of spacetime. What if our entire universe works the same way? This is the core of the holographic principle, that all the information describing everything in our 3D reality, every star, every planet, every thought in your head, might actually be encoded on a two-dimensional surface at the far edges of existence. Imagine a hologram on a credit card, flat to the touch, but when light hits it just right, a vivid 3D image pops out, now scale that up to cosmic proportions. Our entire universe, with its swirling galaxies and infinite depths, could be nothing more than a projection from a flat, distant boundary we can't see or touch. The math behind this is mind-bending. Black holes taught us that the maximum entropy, the total information inside any region of space, doesn't depend on its volume but on the area of its boundary. That's like saying a library's entire collection isn't stored in its countless bookshelves, but etched onto the walls of the building itself. String theorists like Leonard Susskind and Gerard T. Hooft realized this wasn't just a quirk of black holes, it might be a fundamental feature of reality. So how do we test something this extraordinary? Physicists are hunting for evidence in the cosmic microwave background, the oldest light in the universe. If spacetime has a pixelated, holographic nature, there should be subtle noise patterns, tiny fluctuations that don't fit conventional models. Others suggest that gravity's strange weakness compared to other forces could be a clue. In a holographic universe, gravity might leak in from the higher dimensional, real world, making it seem strangely diluted in our projected reality. But here's the beautiful twist: if the holographic principle is true, it doesn't make our existence any less real. The images in a hologram are still vivid, still tangible. The love you feel, the stars you admire, the questions you ponder, they're all part of an immense, interconnected code written on the fabric of the cosmos itself. And that raises an even wilder thought. If reality is a projection, who or what is holding the projector? Imagine floating in the endless void of space, not as a human, not as a living creature at all, but as a lone, fully formed consciousness spontaneously assembled from the random jostling of particles in the emptiness. No body, no past, just a sudden, inexplicable awareness blooming into existence for a fleeting moment before dissolving back into chaos. This isn't a nightmare, it's a real scientific hypothesis called the Boltzmann brain, named after the physicist Ludwig Boltzmann, who wrestled with the strange implications of entropy and time. At its core, the Boltzmann brain thought experiment forces us to confront a bizarre possibility. In an infinitely old universe where particles randomly arrange themselves over unimaginable timescales, the odds of a self-aware mind popping into existence by pure chance might not be zero. Given enough time, trillions upon trillions of years, even the most improbable events become inevitable. A single, disembodied brain with false memories of a life it never lived could spontaneously form in the void, convinced it's a real person in a real world, only to vanish as quickly as it appeared. But here's where it gets even stranger. If Boltzmann brains are possible, they'd vastly outnumber ordinary human minds born through cosmic evolution. Statistically, you are far more likely to be one of these random, momentary flickers of awareness than an actual biological being in a stable universe. So why does our reality feel so consistent? Why do our memories align with a shared past, the arrow of time? The fact that entropy always increases, creating a clear direction from past to future, seems to shield us from this paradox. But some cosmologists argue that in an infinite multiverse, even the laws of physics could fluctuate, making Boltzmann brains not just possible but unavoidable. Critics push back, pointing to the cosmic microwave background and the observed acceleration of the universe's expansion as evidence that our reality isn't an accident. Yet the haunting question lingers: how would we ever know if we were Boltzmann brains? After all, a simulated memory of reading this script would feel just as real as the genuine article. Maybe the only comfort is that if we are random fluctuations, we're at least fluctuations curious enough to ponder our own existence, and that in itself is a kind of marvel. What if our universe is just one bubble in an endless cosmic foam, floating alongside countless others, each with its own unique laws of physics? This is the heart of the Level 1 multiverse theory, a dizzying consequence of cosmic inflation. The idea that our universe underwent an unimaginably rapid expansion in the first fraction of a second after the Big Bang. Alan Guth, the physicist who pioneered inflation theory, realized something extraordinary. If space stretched that quickly once, there's no reason it wouldn't keep happening elsewhere, over and over, like a never-ending chain reaction. Picture a pot of boiling water with bubbles constantly forming, expanding, and drifting apart. Now replace those bubbles with entire universes, each one pinning off from the same initial burst of inflation but evolving independently. In some, gravity might be stronger, snuffing out stars before they can ignite. In others, the speed of light could be slower, turning chemistry into a sluggish dance. And in most, the conditions would be so alien, life as we know it might never arise. The cosmic microwave background, the faint glow left over from the Big Bang, holds tantalizing hints of this. Strange temperature fluctuations and unexplained cold spots in the data could be bruises where our universe bumped against another bubble long ago. Some physicists even speculate that the infamous axis of evil, an eerie alignment of large-scale cosmic structures that defies randomness, might be a fingerprint of neighboring universes tugging at ours through the fabric of space-time. But here's the real kicker. If bubble universes are infinite, then every possible configuration of matter and energy must exist somewhere. Somewhere out there, a version of you is reading this script in a universe where the laws of physics made life inevitable, and another where the very concept of you never emerged at all. The multiverse isn't just a theory, it's a mirror reflecting every possible fate reality could have taken. And that raises a haunting question. In a cosmos this vast, does rare or impossible even mean anything at all? While the Level 1 multiverse imagines bubbles floating in an infinite cosmic foam, String theory takes the idea even further, into landscapes so vast they make bubble universes look simple. Imagine a library where every book isn't just a different story but an entirely different set of physical laws, from the number of dimensions to the strength of gravity. That's the Level 2 multiverse, a dizzying consequence of string theory's hidden dimensions. According to this idea, the tiny, curled-up dimensions theorized in string physics, those 6 or 7 extra spatial layers too small for us to perceive, could exist in trillions of possible configurations. Each one would manifest a unique universe with its own fundamental constants, like cosmic dials randomly set to different values. Somewhere in this landscape, there might be a universe where electromagnetism is too weak for atoms to form, rendering stars and planets impossible. Another might have dark energy so strong galaxies never coalesced at all, and by sheer statistical chance, a few, like ours, would hit the cosmic jackpot with just the right numbers for life to emerge. It's like rolling a million-sided die over and over until you land on the one combination that allows complexity to exist. The Holographic Principle whispers that we must find ourselves in such a universe because the others are barren and unobservable. But then there's the Level 3 multiverse, where reality branches not through space or hidden dimensions, but through time itself. This is the many worlds interpretation of quantum mechanics, where every decision, every quantum fluctuation spawns a new universe. You choose coffee over tea, one universe splits where you sipped Earl Grey. A photon passes through a slit instead of bouncing off. Two realities diverge, one where it behaved as a particle, another as a wave. Unlike the Level 2 landscape, these branches share the same fundamental laws but fork endlessly, creating a fractal tree of alternate histories. The difference between these theories isn't just academic, it reshapes how we view our place in existence. In the Level 2 landscape, we're accidental winners in a cosmic lottery, surrounded by silent, lifeless universes we'll never see. In the many-world scenario, every possible version of us plays out somewhere, from the mundane to the unimaginable. One theory sprawls across hidden dimensions, the other unfolds in the quantum shadows of our own reality. Yet both share a haunting implication. The universe we see might be a single thread in a tapestry so vast it defies comprehension. Whether through shimmering quantum branches or the frozen geometries of string theory, reality could be far richer and far stranger than we ever dreamed. And that raises a question not just about the cosmos, but about us. In a multiverse of infinite possibilities, what does it mean to be this version of you reading this script right now? What if time, the steady ticking of clocks, the unyielding march from past to future, is nothing more than a grand illusion, not a fundamental feature of the universe, but a trick of perception, like shadows dancing on a cave wall? This is the radical proposition of timeless physics, championed by thinkers like Julian Barber, who argue that the flow of time is a human invention, not a cosmic law. Imagine freezing the universe in a single, eternal snapshot, every particle, every galaxy, every thought suspended in a vast, unchanging now, no past. No future, just an infinite collection of moments that our brains stitch together into the sensation of time passing. Loop quantum gravity takes this even further, suggesting space-time isn't smooth and continuous but made of tiny, indivisible chunks, like pixels on a screen. In this framework, time doesn't flow, it jumps, transitioning between these discrete quanta-like frames in a film strip, the smooth motion we experience. Just an illusion created by our limited perception, the same way a spinning propeller appears as a blur. Even Einstein hinted at this when he showed that time slows down near massive objects, proof that it's not universal but malleable, like taffy stretched by gravity. Think about a melting clock in a Dali painting, its face drooping like wet clay. That surreal image might be closer to reality than we realize. At the quantum level, particles don't experience time linearly. They pop in and out of existence, borrow energy from the future, and exist in superpositions where cause and effect blur. The famous double-slit experiment shows particles behaving as if they're aware of future observations, retroactively changing their past behavior. It's as if time is a river that flows both ways, or maybe doesn't flow at all. If time isn't real, why do we perceive it so viscerally? Neuroscientists suggest our brains are prediction machines, stitching together sensory input to create a coherent narrative. Memory isn't a recording of the past, it's a reconstruction edited with every recall. Even now is a delay. The brain takes milliseconds to process stimuli, meaning we're always living slightly behind reality. The present moment, then, is less a point on a timeline and more a trick of consciousness, a hologram projected by the mind. So what replaces time in a timeless universe? Barber proposes nows, isolated configurations of reality that simply are. The illusion of movement comes from jumping between these nows, like flipping through a stack of still images to create animation. Quantum physicist Carlo Rovelli adds that time emerges from relationships between events, heat flowing from hot to cold, apples rotting, stars burning out. Without change, time has no meaning. Here's the mind bender. If time isn't fundamental, free will gets tangled in the threads. Are choices real if the future already exists as a static now? Or is freedom found in accepting that every moment, every version of you, is equally valid, like frames in a cosmic film where every scene plays at once? Whether time is a river, a flickering flame, or a frozen sculpture, one thing's certain: reality is far stranger than clocks and calendars suggest. And that leaves us with a haunting question. If time is just a story we tell ourselves, what other illusions shape the world we think we know? What if consciousness isn't something that emerges from brains, but something woven into the fabric of the universe itself, a fundamental property of reality like gravity or electromagnetism? This is the bold claim of panpsychism, the idea that even the tiniest particles hum with a faint whisper of awareness. Not human thoughts, not emotions, but a raw, primal form of experience, like the difference between a flickering candle and a blazing bonfire. At first glance, it sounds mystical, but some of the world's leading thinkers, from philosopher David Chalmers to neuroscientist Christoph Koch, take it seriously. Because if consciousness is inherent in matter, it solves one of science's greatest puzzles: how subjective experience arises from lifeless atoms. Quantum mechanics might hold the key. In the famous double-slit experiment, particles behave differently when observed, as if they know they're being watched. The Copenhagen interpretation calls this collapse of the wave function, but panpsychists wonder, what if it's not just measurement causing the change, but a rudimentary form of interaction between the particle's proto-consciousness and the observer's mind? Even stars and galaxies could play a role. Astrophysicists have found eerie correlations between star formation rates and the presence of conscious observers like us. It's as if the universe, on some level, wants to be seen like a cosmic version of the tree falling in the forest with no one to hear it. Critics dismiss this as poetic thinking, but the math gets stranger. Integrated information theory, a leading model of consciousness, suggests that any system with enough interconnected complexity, whether a brain, a computer, or even a galaxy's swirling arms, could harbor some degree of subjective experience. Picture a supermassive black hole's accretion disk, its particles trillions of times more densely connected than neurons in a human brain. Could it feel something? Not joy or pain, but a vast, slow-motion hum of existence. The Milky Way might not compose symphonies, but neither does a jellyfish, yet we don't deny it has some basic response to light and touch. Here's the radical implication. If panpsychism is true, the universe isn't just alive, it's awake. Every collision of asteroids, every pulse of a quasar, every photon streaking through the void might carry a flicker of inner experience. Consciousness wouldn't be a rare accident on tiny wet planets. It'd be as universal as space-time itself. And that changes everything, because if the cosmos is watching itself through our eyes, then asking, "Are we alone?" misses the point entirely. The real question is, how long has the universe been dreaming of being known? What if the Big Bang wasn't the beginning of everything, but the echo of a collapse, a cosmic sigh from a universe that came before? Black hole cosmology turns our understanding of reality inside out, suggesting our entire universe might exist within the event horizon of a black hole from a parent cosmos. Picture a Russian nesting doll where each layer hides a deeper, stranger world. When matter falls into a black hole, it doesn't just vanish. According to Einstein's equations, the extreme gravitational forces stretch and compress it into an infinitely dense singularity. But what if that singularity doesn't mark the end? What if it's a bridge, a tunnel to somewhere new? Roger Penrose's conformal cyclic cosmology takes this even further. He proposes that universes don't just die, they recycle. When our cosmos reaches heat death, all energy evenly spread, all stars burned out black holes will evaporate via Hawking radiation, leaving behind a sea of massless particles. At this point, time and distance lose meaning. The universe becomes conformally invariant, a blank slate indistinguishable from the singularity of the next Big Bang. In this model, the cosmic microwave background, the afterglow of our universe's birth, might carry imprints of black hole collisions from the previous cycle, like shadows of a forgotten age. But how could a black hole birth a universe? The math reveals eerie parallels. A collapsing star's singularity and the Big Bang's initial conditions share uncanny similarities. Both are points of infinite density where known physics breaks down. Some theorists suggest the Big Bang was a white hole, the hypothetical opposite of a black hole where matter explodes outward uncontrollably. If true, every black hole in our cosmos might contain a budding universe expanding in its own space-time bubble, forever hidden from our view. Astronomers have even searched for fingerprints of this theory. The cosmic microwave background shows mysterious Hawking points, circular patches of unexpected temperature variation. Penrose argues these could be radiation scars from supermassive black holes that evaporated in the previous universe, their final breaths imprinted on our sky like cosmic graffiti. Skeptics counter that these patterns could be random fluctuations, but the idea lingers. What if we're standing on the shoulders of cosmic giants, the remnants of civilizations that lived and died in a universe we'll never see? Here's the profound twist. If black holes are universes in disguise, then every galaxy's heart might harbor an entire cosmos. Our Milky Way's supermassive black hole, Sagittarius A, could contain galaxies, stars, and maybe even beings staring back at their own night sky, wondering if they too live inside a black hole. It's a hall of mirrors stretching to infinity, where each reflection asks the same haunting question: how deep does the rabbit hole go? And if we're inside someone else's collapsed star, does that make us the ashes of their ending or the embers of a new beginning? What if reality doesn't run on physics as we know it, but on code? Imagine the universe as a vast, humming supercomputer, where every quark, every galaxy, is just a pixel in some unfathomable cosmic program. This is the radical premise of digital physics, a theory that rewrites the rules of existence not in terms of particles or waves, but ones and zeros. At its core, the idea is simple. The universe isn't just like a computer, it is an intricate computational process unfolding step by deterministic step. Stephen Wolfram, the mathematician behind cellular automata, stumbled onto this while playing with grids of black and white squares governed by simple rules. Even with basic instructions, these systems generated staggering complexity: spirals, fractals, even structures resembling organic life. Wolfram realized something profound. Maybe nature's deepest laws aren't equations at all, but algorithms. The intricate patterns of snowflakes, the branching of veins in leaves, even the clustering of galaxies, what if they're all emergent behaviors from tiny, localized computations? Then there's Edward Fredkin's digital philosophy, which takes this further. Fredkin argued that information isn't just a tool for describing reality, it is reality. Atoms, energy, even time might just be data structures in a universe-sized processor. Think of Minecraft, where every block is a discrete unit governed by rules, except in this case, the blocks are Planck-scale pixels, the smallest possible bits of spacetime. Movement, just pixels updating their state, gravity, data propagating through the grid. Even quantum weirdness could be glitches or rounding errors in the cosmic calculation. But how would we test such a wild idea? Some physicists search for evidence in the fine-grained structure of spacetime. If the universe is digital, there should be a fundamental resolution limit, a smallest possible distance or time interval, like the pixels on a screen. Experiments with ultra-precise atomic clocks and particle colliders hunt for these telltale hints of discreteness, tiny stutters in the smooth flow of reality. Others look to black holes, theorizing that their event horizons might act like cosmic hard drives, with information storage limits governed by surface area rather than volume, echoing how computer memory works. The implications are staggering. If digital physics is correct, free will might just be an illusion, a feeling generated by complex computations we can't perceive. The laws of physics, mere subroutines in a program we're all running inside. Even consciousness could be a kind of self-referential algorithm, a loop in the code that creates the sensation of I. Yet here's the twist: if we're living in a computational universe, who or what is the programmer? The answer might be nobody. Wolfram suggests the system could be self-generating, with simple rules giving rise to endless complexity without any external input. Or perhaps we're someone else's experiment, a simulation running on hardware we'll never see. Either way, one thing's certain: reality just got a whole lot weirder, and a whole more beautiful when you realize the cosmos might not just calculate. It counts. If inflation, the explosive expansion that jump-started our universe, never actually stopped, what would that mean for reality? Picture a volcano erupting not once, but endlessly, each burst of molten rock birthing new landmasses that drift away into the void. Now replace the volcano with spacetime itself, and the lava with entire universes, each one puffing into existence in an infinite chain reaction. This is the heart of eternal inflation, a theory where the Big Bang isn't a singular event in the past, but an ongoing process, seething and churning even as you read these words. Russian physicist Andrei Lin's chaotic inflation model paints a universe far wilder than we ever imagined. Instead of a neat, uniform expansion, think of spacetime as a boiling ocean, with quantum fluctuations creating rogue waves that swell into pocket universes. Each of these bubbles nucleates with its own physics, expanding at breakneck speed while new bubbles form in the gaps between them. The result, a self-replicating fractal cosmos, where every region that cools into stability is surrounded by an eternally inflating sea of raw potential. The visuals are staggering. Imagine zooming out from our universe like a cosmic microscope, revealing a honeycomb of bubble universes, each one a self-contained reality with its own laws. Some might have stronger gravity, crushing stars into black holes before life can emerge. Others could be so diffuse, matter never clumps into galaxies at all. And in between them, the inflationary field rages on, stretching spacetime so fast that light from neighboring bubbles can never reach us. We're not just isolated, we're surrounded by an infinity of alien physics we'll never witness. But how does inflation not stop? It all comes down to energy. The inflationary field is like a mountain covered in snow, where our universe represents a single snowball that rolled downhill and settled in the valley. But most of the snow remains up high, waiting to avalanche. Quantum effects keep pushing new regions over the edge, ensuring the process never truly ends. Lin's genius was realizing that this isn't a bug, it's the feature. Inflation isn't something that happened, it's something that keeps happening, a perpetual engine of creation. Critics argue this makes the theory untestable, but there are clues. If our bubble universe collided with another in the distant past, the crash might have left scars in the cosmic microwave background, strange temperature variations or circular patterns. Some researchers claim to have spotted these anomalies, though debate rages. Others suggest that the multiverse's fractal structure could imprint on the distribution of galaxies, creating vast, unnatural voids in the cosmic web. Yet eternal inflation's real power isn't just in spawning universes, it's in redefining what beginning even means. If inflation is endless, then time itself might stretch backward infinitely with no true starting point. Our Big Bang becomes a local event, a single spark in an eternal firestorm, and that leaves us with a humbling thought. If reality is still being born, still multiplying, still experimenting with new laws in distant bubbles, then the universe isn't just vast, it's alive, a growing, breathing entity rewriting its own rules with every passing moment. What if our universe isn't floating in empty space but stuck to something? Picture a soap bubble drifting through the air, its shimmering surface stretching thin and fragile. Now imagine that bubble isn't just a sphere, it's a vast three-dimensional membrane or brain vibrating in a hidden dimension we can't see. This is the mind-bending premise of brain world theory, a radical idea from string theory that reimagines our entire cosmos as a single slice of something much, much bigger. String theory suggests the universe isn't made of point-like particles but tiny, vibrating strings, threads of energy so small they'd make an atom look like a galaxy in comparison. But for the math to work, these strings need more room than our familiar 3 dimensions. They require extra spatial dimensions, 6 or 7 of them, curled up so tightly we'd never notice. Brain world theory takes this further, proposing that our entire universe is a 3-dimensional brain drifting through a higher dimensional space called the bulk. Think of it like a slice of bread floating in an infinite loaf, utterly unaware of the other slices around it. Here's where it gets wild. If other brains exist just a hair's breadth away in these hidden dimensions, they could be entire universes with their own stars, planets, and laws of physics forever out of reach. Even stranger, the Big Bang itself might have been caused by a collision between 2 of these brains. Picture 2 sheets of paper smacking together in midair, unleashing enough energy to birth a cosmos. The ripples from that crash could still echo in the cosmic microwave background, hidden in the faint temperature variations we observe today. But how could we ever detect these invisible dimensions? Gravity might hold the key. In some brain world models, gravity isn't confined to our brain like light and matter. It leaks into the bulk, explaining why it's so weak compared to other forces. Particle accelerators like the Large Hadron Collider could, in theory, spot evidence of this. If tiny ripples in gravity reveal hidden dimensions, high-energy collisions might produce particles that momentarily vanish into the bulk before reappearing, like stones skipping across a pond's surface. The implications are staggering. If brains drift close enough, their gravity could tug at our universe, warping galaxies without any visible cause, a possible explanation for dark matter. And if another brain brushed against ours today, the energy released could rewrite physics in an instant, a cosmic reset button we'd never see coming. Yet the most haunting thought isn't about collisions, it's about isolation. If we're stuck on our brain like ants on a leaf, forever cut off from the vastness of the bulk, how many universes are out there just beyond our fingertips? How many versions of us exist on other membranes, living lives nearly identical to ours or so alien, we'd never recognize them as kin? Brain world theory doesn't just expand the universe. It turns it into a library of realities, each page pressed so close we'll never know how many stories remain unread. You wake up one morning, step into the shower, and suddenly the water turns scalding hot. For a split second, your body recoils in pain, your heart lurches, then nothing. The temperature corrects itself and you shake it off as a weird glitch in the pipes. But what if, in that moment, you did die, just not in this version of reality? This is the spine-tingling premise of quantum immortality, a thought experiment that twists Schrödinger's famous cat into a mirror for our own existence. At its core, quantum immortality asks, what happens to you when the many worlds interpretation of quantum mechanics plays out? In Schrödinger's original paradox, a cat in a box is both alive and dead until observed, a metaphor for how particles exist in superpositions until measured. But if every quantum possibility spawns a new universe, then there's always a branch where the radioactive decay doesn't trigger the poison, where the gun jams, where the car swerves just in time. From your perspective, you'd only ever experience the timelines where you survive, no matter how improbable the odds. Think of it like flipping a coin 100 times and getting heads every single time. Statistically, it's absurd unless every tail's outcome branches into a universe where you're not there to count the result. You're not lucky, you're just the version of yourself that has to keep observing, like a cosmic game of musical chairs where the music never stops for you. Russian physicist Max Tegmark illustrated this with a grim but fascinating scenario. Imagine a futuristic firing squad where a quantum trigger gives the gun a 50% chance to fire. After 1,000 attempts, statistically, you should be dead. Yet from your first-person view, you'd always find yourself alive, bewildered as the gun keeps miraculously jamming. The existential implications are dizzying. If consciousness naturally migrates to surviving branches, does that mean we're all effectively immortal from our own perspective? Could people in comas or near-death experiences be momentarily slipping into adjacent timelines? Some theorists even speculate that quantum immortality might explain glitches in the matrix, those eerie moments when you're certain something changed, a missing building, a suddenly different scar because, well, it did in another branch. But here's the chilling counterpoint. If this theory holds, everyone around you could be experiencing their own quantum survival, making tragedies and accidents seem selectively cruel. Your loved ones might vanish from your reality while continuing on in others, their consciousnesses never experiencing the end you witness. It's a lonely kind of immortality, one that trades cosmic fairness for sheer persistence. Critics argue this is solipsism disguised as physics, that probability doesn't bend to preserve subjective experience. Yet the math of many worlds doesn't discriminate, it just calculates branches. Whether you find comfort or horror in quantum immortality might come down to this. Is it more terrifying to think death is final, or that existence is a labyrinth with no exit, only endless turns where you always find the path forward? Schrödinger's cat was a paradox, but the human staring back at it from the box, that's the real mystery. Imagine this, you're sitting at home, scrolling through your phone, when suddenly the walls start to flicker like a dying light bulb. The air hums with an unfamiliar energy. Before you can react, your hand dissolves into mist, then your arm, then the entire room. Not in flames, not in smoke, but into something entirely new and unrecognizable. No sound, no pain, just existence itself rewriting its rules in an instant. This isn't science fiction. It's the nightmare scenario of false vacuum decay. A theory that suggests our universe might be perched on the edge of oblivion, one quantum hiccup away from total annihilation. At the heart of this terrifying idea is the Higgs field, the invisible cosmic molasses that gives particles their mass. For decades, physicists assumed this field was stable, a gentle valley in the landscape of reality. But recent calculations suggest something darker. We might not be in the valley at all, but on a fragile ledge somewhere higher up. Think of a marble resting on the rim of a bowl. It looks steady, but the slightest nudge could send it rolling into the depths. In cosmic terms, that nudge could be a random quantum fluctuation, a tiny burp in the fabric of spacetime that tips the Higgs field into a lower, more stable state. The moment that happens, a bubble of true vacuum would form, expanding at the speed of light in all directions. Inside this bubble, the laws of physics as we know them cease to exist. Atoms gone, light redefined. The very concept of matter becomes meaningless. You wouldn't see it coming. 1 nanosecond, everything's normal. The next, an undetectable wall of annihilation sweeps through the solar system, leaving nothing recognizable in its wake. Astoundingly, this isn't speculation, it's grounded in the math. Experiments at the Large Hadron Collider suggest the Higgs mass sits in a precarious range where vacuum instability isn't just possible, but statistically likely over vast timescales. The universe might be like a sandcastle at high tide, seemingly solid until the right wave hits. Some theorists argue this could have already happened elsewhere, with collision bubbles racing toward us from distant galaxies. Others find solace in the sheer slowness of quantum decay. It might take trillions of years for the dice to roll the wrong way. But here's the twist: if a decay bubble is coming, we couldn't stop it, hide from it, or even warn others. The change would be too fundamental for any signal to outrun it. Civilizations 1,000 light-years away might have already vanished, their final broadcast showing nothing unusual before the screen went blank. The eerie silence of the cosmos, the Fermi paradox, might have its answer in these silent, shimmering bubbles of rewritten reality. Yet this doom isn't guaranteed. The universe has survived 13.8 billion years so far, suggesting either we're lucky or our vacuum is more stable than we fear. Some models even propose that dark energy acts as a shield, propping up our precarious perch. But the haunting question lingers: are we living in the calm before an unthinkable storm, or is reality far more resilient than its equations suggest? One thing's certain: the Higgs field doesn't care about our fears. It simply is, and in its silent, invisible depths, the fate of all existence may already be written. Time crystals sound like something ripped from the pages of a sci-fi novel. Crystalline structures that pulse and shimmer not just in space, but in time itself, dancing to the rhythm of the universe like a metronome set to eternity. But this isn't fantasy. Nobel Prize-winning physicist Frank Wilczek proposed these bizarre structures as a radical new phase of matter, one that defies our most fundamental assumptions about motion and energy. Picture a snowflake that doesn't just sit frozen in space, but one that cycles through its patterns over and over forever without any energy input. A perpetual motion machine, not of gears and levers, but of atoms and spacetime. Wilczek's insight was this: just as regular crystals break the symmetry of space by repeating their atomic arrangements in predictable patterns, time crystals break the symmetry of time, oscillating between states with a regularity that seems to thumb its nose at entropy. Imagine a cosmic clock that ticks not because it's wound up, but because the fabric of reality itself forces it to keep perfect, unchanging time. In 2016, scientists brought this idea to life in the lab, using chains of ytterbium ions doused with laser pulses. The ions didn't just react to the lasers, they started flipping their spins at a rhythm different from the pulses, as if the system had a mind of its own. That's the hallmark of a time crystal, a structure that finds its own beat in the chaos. But here's where it gets cosmic. What if time crystals aren't just lab curiosities, but natural phenomena woven into the universe? Some theorists speculate that neutron stars, those ultra-dense corpses of dead suns, might harbor time crystalline structures in their crushing interiors where gravity warps spacetime into knots. Others wonder if dark matter, that elusive ghost haunting the cosmos, could exist in a time crystalline phase, pulsing silently in the void between galaxies. Even the vacuum of space itself might seethe with microscopic time crystals, fleeting ripples of order in the quantum foam. Yet the real magic lies in what time crystals imply about the nature of reality. Perpetual motion is supposed to be impossible, a dream shattered by the laws of thermodynamics. But time crystals don't violate these laws, they sidestep them like a dancer gliding across a frictionless floor. They don't create energy, they just redistribute it in an endless loop, a cosmic game of hot potato where the music never stops. This isn't just a new kind of matter. It's a new kind of time, one where the arrow we're so used to might not be the only direction causality can point. So what happens if we scale this up? Could the universe itself be a kind of time crystal, cycling through states in a grand, eternal rhythm? Some cosmologists play with the idea of a cyclic cosmos, where big bangs and big crunches repeat like the ticking of a clock. Time crystals hint at a deeper truth, that beneath the chaos, reality might have a heartbeat, steady and silent, ticking long after stars burn out and civilizations fade. And if that's true, then time isn't just a river flowing forward. It's a mosaic, a kaleidoscope of moments forever folding back on themselves, echoing into the dark. What if the universe isn't just shaped like a brain? What if it is one? Astronomer Franco Vazza and neuroscientist Alberto Felletti made a discovery so uncanny, it blurs the line between the cosmic and the microscopic. When they superimposed images of galaxy clusters onto slices of the human brain, the resemblance wasn't just poetic, it was mathematical. The branching filaments of the cosmic web, those vast rivers of dark matter and gas connecting galaxies across billions of light years, mirrored the dendritic structures of neurons with eerie precision. Both systems, one spanning the unimaginable vastness of space, the other crammed into the cramped confines of a skull, followed the same patterns of growth, the same physics of connectivity. It's as if the universe built its largest and smallest structures using the same blueprint. Zoom in closer and the parallels grow even stranger. Just as neurons communicate through synaptic signals, galaxies exchange gas and energy along their filamentary bridges. The universe's synapses might be the shock waves and magnetic fields threading through these cosmic tendrils, orchestrating the flow of matter like neurotransmitters firing across a neural gap. Even the numbers align. A human brain contains around 69 billion neurons, while the observable universe hosts roughly 100 billion galaxies. Coincidence or something deeper? A hint that complexity, whether biological or cosmological, converges on a universal architecture. Critics argue this is just pareidolia, the human tendency to see familiar shapes in randomness like faces in clouds. But Vazza's team didn't stop at visuals. They ran quantitative analyses comparing the distribution of matter in galaxy clusters to neural networks. The results were startling. Both systems showed similar levels of clustering, with small, dense regions nested within larger, sparser ones. Even the information storage capacity lined up. A single human brain can hold an estimated 2.5 petabytes of data, roughly equivalent to the amount of information encoded in the large-scale structure of the universe. So is the cosmos a literal brain? Not quite. But the resemblance suggests something profound, that the laws governing growth and organization, whether in living tissue or the void of space, might emerge from universal principles we're only beginning to grasp. Complexity theorists call this scale invariance, the idea that patterns repeat across wildly different sizes, from snowflakes to coastlines to stock market fluctuations. In this light, the universe isn't a conscious entity, but a reflection of how information and structure evolve under certain rules, yet the implications linger. If the universe organizes itself like a neural network, could it also process information? Some theorists speculate that dark matter, the invisible scaffolding of the cosmos, might form a kind of dark internet, transmitting signals we can't detect. Others wonder if black holes function as cosmic nodes, warping space-time in ways that resemble synaptic firing. It's a dizzying thought that every star, every planet, every flicker of light might be part of a computation so vast we're just now glimpsing its syntax. Whether coincidence or cosmic design, this theory forces us to confront a humbling possibility that the universe might not just contain minds but resemble one. Not as a thinking entity, but as a system where connection is the fundamental currency, where the dance of matter and energy follows rhythms written into the fabric of existence itself. And if that's true, then peering into the night sky isn't just astronomy, it's neuroscience on the grandest scale imaginable. What if gravity, the invisible force holding planets, stars, and galaxies together, isn't a fundamental force at all, but a side effect of something far stranger happening at the quantum level? Picture two entangled particles, their fates linked across vast distances in a way Einstein famously called spooky action at a distance. Now imagine that their connection isn't just a shared quantum state, but an actual bridge in spacetime itself, a tiny wormhole threading through the fabric of reality. This jaw-dropping idea, known as ER equals EPR, suggests that entanglement and wormholes are two sides of the same cosmic coin. The theory's name comes from two groundbreaking papers, Einstein and Rosen's 1935 work on wormholes nicknamed and Einstein-Podolsky, and Rosen's earlier paper on quantum entanglement, EPR. For decades, these concepts seemed unrelated, one describing bizarre particle behavior, the other hypothetical tunnels through spacetime. But in 2013, physicists Leonard Susskind and Juan Maldacena made a radical leap. What if every pair of entangled particles is invisibly connected by an infinitesimal wormhole? Not a tunnel you could travel through, but a geometric thread binding them at the deepest level of reality. Here's where it gets mind-bending. Black holes, those cosmic vacuum cleaners, might be the key to understanding this link. When two black holes become entangled, their interiors could theoretically be joined by a wormhole, a scenario dubbed an Einstein-Rosen bridge. The math reveals something astonishing. The wormhole's geometry perfectly mirrors the quantum entanglement between the black holes. It's as if spacetime itself emerges from the quantum connections between particles, weaving the universe together stitch by stitch. Think of it like a knitted sweater. The yarn is quantum entanglement, the loops and knots forming the fabric of spacetime. Pull one thread, and the whole structure tightens, just as measuring one entangled particle instantly affects its partner. In this view, gravity isn't some separate force. It's the collective effect of countless tiny quantum threads pulling the cosmic sweater into shape. Even empty space might fizz with these hidden connections, a seething network of microscopic wormholes we're only beginning to map. But how could we ever test such an abstract idea? Experiments with quantum computers offer tantalizing hints. By simulating entangled particles, researchers have observed behavior that mirrors wormhole dynamics, information seemingly teleporting between systems in ways that resemble spacetime shortcuts. Other clues might hide in the event horizons of black holes, where quantum information and geometry collide. If ER equals EPR holds, then probing the boundary of a black hole could reveal secrets about the entanglement structuring the cosmos. The implications rewrite our understanding of reality. If entanglement builds spacetime, then the universe isn't just held together by gravity, it's held together by information. Every star, every atom, every fleeting thought might exist because of an immeasurable web of quantum links, each one a stitch in the tapestry of existence. Suddenly, the vast emptiness of space feels less like a void and more like a living, breathing network, one where every connection, no matter how small, helps shape the grand geometry of everything. Phantom energy isn't just a mysterious force pushing the universe apart. It could be the wrecking ball that tears reality apart at the seams. Imagine dark energy not as a gentle nudge, but as a runaway engine that grows stronger over time, accelerating expansion until galaxies, stars, even atoms are ripped to shreds in a cataclysm cosmologists call the Big Rip. This isn't some distant, abstract threat. If phantom energy is real, the collapse could happen within a finite timeline, turning the cosmos into a graveyard of scattered particles drifting in infinite, empty darkness. The horror of this scenario lies in the numbers. dark energy currently makes up about 68% of the universe's energy budget, driving its accelerated expansion. But phantom energy is a hypothetical, extreme form of dark energy with a terrifying property. Its density increases as space stretches. Picture a rubber band that gets harder to pull the more you stretch it, except instead of snapping back, it keeps stretching until it disintegrates. In this case, the rubber band is space-time itself. Here's how the nightmare unfolds. First, galaxy clusters would fly apart as the space between them expands faster than light can bridge the gap. Nearby galaxies like Andromeda, currently on a collision course with the Milky Way, would vanish over the cosmic horizon, their light stretched into undetectable infrared whispers. Next, gravity would lose its grip. Stars would detach from their galaxies, drifting into the void like candles snuffed out by the wind. Then, planetary systems would unravel, Earth torn from the Sun's orbit, continents ripped from their tectonic plates. But the true horror comes in the final moments. Minutes before the end, phantom energy's grip would overcome atomic bonds. Mountains would dissolve into clouds of loose particles. Your body, your phone, the air you breathe, all would vaporize into a chaotic mist of quarks and electrons. Even atomic nuclei, held together by the strongest force in nature, would splinter apart. The universe wouldn't just die, it would be erased, leaving behind a vacuum so empty, not even time would have meaning. Could this really happen? Observations of distant supernova and the cosmic microwave background suggest dark energy's strength has remained constant so far. But if phantom energy exists, its fingerprints might hide in the way galaxies cluster at the largest scales. Some theorists argue that the Big Rip could be triggered if dark energy's equation of state, a measure of its pressure-to-density ratio, dips below a critical threshold. Others speculate that phantom energy could be tied to quintessence, a dynamic field that might someday flip from benign to catastrophic, the chilling takeaway. If the cosmos is a ticking clock, phantom energy could be the pendulum swinging toward midnight. And once it starts, there's no off switch, just an inexorable unraveling of every structure, every law, every memory the universe ever held. Against such a force, even black holes wouldn't be safe. Their event horizons would stretch and shatter, spilling their secrets into the void. The Big Bang birthed reality. The Big Rip wouldn't just end it, it would excise the very concept of existence from the cosmic ledger. What if the death of our universe isn't an ending, just a reset button pressed by black holes? Sir Roger Penrose's cyclic conformal cosmology, or CCC, spins the traditional Big Bang narrative on its head, proposing an eternal cycle where universes are endlessly reborn from the ashes of their predecessors. In this model, the distant future isn't a cold, dark oblivion. It's the cosmic equivalent of a phoenix waiting to ignite. The key lies in black hole singularities, those infinitely dense knots of spacetime where gravity becomes so intense, even Einstein's equations break down. Penrose realized something extraordinary. The conditions inside a singularity, infinite density, zero volume, are mathematically identical to those at the Big Bang. It's as if the universe left behind a blueprint for its own rebirth in the very objects we thought were its tombs. Picture the far future, trillions of years from now. All stars have burned out. Black holes have evaporated via Hawking radiation, leaving behind a sea of massless particles drifting in an ever-expanding void. Time and distance lose meaning as the universe approaches what physicists call heat death, a state of maximum entropy where no energy remains to power change. But here's Penrose's twist. At this point, the cosmos becomes conformally invariant, a geometric state where scales no longer matter. An infinite universe and a single point become mathematically indistinguishable. The universe doesn't just end, it folds in on itself, shedding its worn-out dimensions like an old skin, ready to trigger a new Big Bang from the very same conditions that birthed ours. The visuals are mind-bending. Penrose diagrams, those intricate maps of space-time, reveal how eons of cosmic history compress into elegant, looping shapes. Black hole singularities from our universe become the seeds of the next, their infinite densities bridging the gap between cycles. Imagine a cosmic hourglass where the sand of one era pours into the neck of a singularity, only to emerge as the pristine, energetic dust of a fresh cosmos. This isn't science fiction. The math suggests that gravitational waves from colliding black holes might carry imprints of previous universes, faint whispers of civilizations lost to time. But how could we ever detect evidence of a universe before ours? Penrose points to the cosmic microwave background, the afterglow of the Big Bang. Strange, circular patterns called Hawking points scatter across this ancient light anomalies that defy conventional cosmology. These could be scars left by supermassive black holes that evaporated in the previous cycle, their final bursts of energy stamped onto the newborn universe like cosmic fingerprints. Skeptics argue these patterns could be random noise, but if Penrose is right, we're holding a postcard from a reality long gone, a message in a bottle washed ashore from beyond time. The beauty of CCC isn't just in its elegance, it's in the questions it forces us to ask. If universes recycle, do the laws of physics evolve with each iteration? Could life, intelligence, even consciousness emerge again and again, playing out variations on a theme across eternity? And most hauntingly, if this cycle has happened before, how many times? The answer might lie in the silent geometry of spacetime itself, a riddle written in the language of singularities, waiting for us to decipher its code. What if reality doesn't just exist but waits for us to look before deciding what it is? John Archibald Wheeler, the physicist who coined the term black hole, proposed a universe far stranger than we ever imagined, one where the cosmos isn't just observed but shaped by observation itself. This is the participatory universe, a radical twist on quantum mechanics where the past isn't set in stone until the present moment locks it into place. Picture a cosmic game of 20 questions where every answer you get doesn't just reveal reality, it creates it. Wheeler's most mind-bending demonstration of this is the delayed choice experiment, a quantum riddle that defies common sense. Imagine firing a single photon toward a beam splitter, giving it the choice to travel two paths like a fork in the road. If you measure which path it took, it behaves like a particle, one concrete trajectory. But if you don't measure, it acts like a wave, taking both paths simultaneously. Here's the twist: you can wait until after the photon has already made its choice to decide whether to measure it or not. Somehow, the photon retroactively changes its past behavior based on your future decision. It's as if the universe refuses to write its history until you've asked the right question. Now scale this up to cosmic proportions. Wheeler suggested that even galaxies might hang in quantum limbo until observed, their light waves unresolved possibilities until a conscious mind, perhaps a stargazer on a distant planet, forces them to choose a definite state. In this view, the Big Bang itself might be a quantum event that's only now solidifying as we reconstruct it through telescopes. The universe doesn't just unfold, it unfolds backward, stitching together causality like a tailor working from the finished suit back to the first stitch. But how can observation, something as mundane as looking at a star, rewrite cosmic history? Quantum decoherence offers a clue. When a quantum system interacts with its environment like light hitting a telescope, its wave function collapses from a haze of probabilities into a single, measurable outcome. Wheeler took this further, proposing that the universe is a vast, self-excited circuit, where observation at any point sends ripples backward and forward through time, weaving reality into existence. Picture a cosmic version of a choose-your-own-adventure book, where every measurement flips not just the next page, but edits the ones you've already read. Critics argue this veers into solipsism, but Wheeler's point wasn't that individuals shape reality alone. Rather, the universe participates in its own creation through an endless chain of observations, from photons hitting retinas to detectors recording cosmic rays. Even the first primitive atoms observed each other, collapsing quantum uncertainties through sheer proximity. The participatory universe isn't about human centrality. It's about the interconnected web of events that crystallize the cosmos moment by moment. So what does this mean for us? If Wheeler was right, then peering into the night sky isn't a passive act. It's a cosmic collaboration, a dance where the universe reveals itself only when asked. The light from distant stars may have traveled billions of years, but in some profound sense, it was waiting for you to look up and give it meaning. And that raises a humbling thought. In a universe that thrives on participation, the greatest discoveries might not be out there among the stars, but in the simple, staggering act of paying attention. Deep beneath the equations of particle physics, something strange is whispering an elegant symmetry so perfect, it could rewrite our understanding of reality itself. Supersymmetry, or SUSY, isn't just a theory. It's a cosmic game of hide and seek where every particle we know has a secret twin lurking just beyond our perception. Imagine a mirror world where electrons dance with shadowy selectrons, quarks pair with squarks, and even photons have mysterious photino partners. These superpartners aren't just duplicates, they're the missing puzzle pieces that could explain why the universe weighs what it does, why gravity is absurdly weak compared to other forces, and what dark matter might actually be. The beauty of SUSY lies in its symmetry. Just as matter and antimatter complete each other like cosmic yin and yang, superpartners balance the quantum scales in ways that make physicists' hearts race. Here's the kicker. These particles wouldn't just fill gaps in our models, they'd solve the hierarchy problem. The baffling mystery of why gravity is 10 trillion times weaker than electromagnetism. If superpartners exist, they'd cancel out quantum fluctuations that otherwise make the Higgs field's energy explode to impossible levels. Think of it like a tightrope walker with an invisible counterbalance. Without it, the universe's delicate framework would collapse under its own weight. But where are these superpartners? If they're real, why haven't we spotted them? SUSY suggests they're far heavier than their ordinary counterparts, decaying almost instantly into detectable particles, like cosmic will-o'-the-wisps flickering at the edge of perception. The Large Hadron Collider has hunted for them, sifting through debris from proton collisions at near-light speeds. So far, no definitive trace, yet SUSY isn't dead, it's just shape-shifting. Some theorists argue superpartners might be stealthy, barely interacting with our detectors. Others propose they exist in hidden spatial dimensions, curled up so tightly, their effects only bleed into our world as faint gravitational whispers. The implications dizzy the mind. If SUSY is true, dark matter could literally be all around us, not as some exotic unknown, but as neutralinos, the lightest superpartners, drifting through your body right now like cosmic ghosts. Even the fabric of space-time might vibrate with hidden symmetries, resonating in harmonies we're only beginning to hear. SUSY isn't just a theory of particles. It's a love letter to the universe's hidden order, a mathematical sonata where every note has its echo. And if we one day catch that echo, in a detector's blip, a galaxy's spin, or the hum of the quantum vacuum, we won't just find new particles, we'll glimpse the signature of a reality far more interconnected, more elegant than we ever dared to dream. Imagine a quantum particle in a lab, existing in a blur of possibilities until observed when it snaps into focus like a camera shutter clicking. Now picture this happening not just in controlled experiments, but everywhere, all at once, trillions of times per second, a constant winnowing of maybes into certainties. This is the essence of quantum Darwinism, a theory that explains why we don't live in a world where cats are simultaneously dead and alive, where chairs vanish when we glance away. It's nature's way of voting on reality, not through conscious observers, but through the relentless interactions of particles with their environment, a process called decoherence. Think of it like a cosmic game of telephone played by the entire universe. When a quantum system, say, an electron in a molecule, interacts with its surroundings, photons, air molecules, even stray magnetic fields, information about its state gets copied and broadcast like ripples in a pond. The most stable, resilient versions of that state survive this interaction, while fragile superpositions fade like whispers drowned out by noise. Over countless iterations, only the fittest quantum states persist, proliferating through the environment like genes in a population. This is quantum Darwinism in action, not survival of the fittest, but reality of the fittest. Visualize this as a tree of life for quantum possibilities. At the roots, you have the raw quantum soup, countless overlapping states branching chaotically. As decoherence prunes this tree, entire branches vanish, leaving only the sturdiest configurations to grow into the world we perceive. A spinning electron doesn't just choose up or down randomly. Its interaction with the environment amplifies one outcome while erasing others, like a sculptor chiseling away marble to reveal the statue within. The universe isn't just observing itself, it's selecting which observations stick. But here's the kicker, we're not passive witnesses to this process. Our bodies, our devices, even the air we breathe are part of the decoherence machine, constantly measuring and reinforcing stable reality. When you touch a table, the atoms in your hand don't just feel solidity. They participate in a chain reaction that collapses the table's quantum fuzziness into definite form. The chair you're sitting on exists not because it was always there, but because trillions of quantum interactions voted unanimously for its persistence. Critics argue this pushes the measurement problem onto the environment. How does decoherence explain why one outcome wins over another? Proponents counter that it's not about why, but how often. Stable states replicate their information more efficiently, like memes going viral in the noise of the cosmos. A single photon bouncing off an object carries a fragment of its state. Multiply that by sextillions of interactions, and you get a consensus reality etched into existence. The implications are profound. If quantum Darwinism holds, the world we see isn't the only possible one, just the version that best survived the quantum gauntlet. Alternate histories, parallel worlds, even fleeting glitches in the matrix might exist briefly before being voted off the island by decoherence. It's a humbling thought. Reality isn't handed down from on high. It emerges from the chaos, one interaction at a time, shaped by the same forces that make trees grow and stars shine. And in that emergence, we find not just how the universe works, but how we, its participants, help write the story. What if the Big Bang wasn't the beginning, but the echo of a collision between cosmic giants? The ekpyrotic universe theory, proposed by physicists Paul Steinhardt and Neil Turok, turns the traditional origin story inside out, replacing a singular explosion with an endless cycle of cosmic collisions. Imagine two immense parallel membranes, or brains, floating in a higher dimensional space, separated by a gap thinner than an atom. These aren't just abstract sheets, they're entire universes, each one a three-dimensional reality teeming with galaxies, stars, and perhaps even life. Now picture them drifting closer, drawn together by an invisible force, until bang, they smash into each other with enough energy to reboot existence itself. This isn't science fiction. The math behind the ekpyrotic model suggests that such a collision would release energy identical to what we observe in the Big Bang's afterglow, the cosmic microwave background. But here's the twist. Instead of a fiery singularity, the energy disperses smoothly across the brains, creating the conditions for matter, light, and structure to form without the chaotic inflation of traditional cosmology. Think of it like two sheets of paper smacking together in midair. The moment of impact sends ripples racing across their surfaces, ripples that, in cosmic terms, become the seeds of galaxies and cosmic webs. And then, like pendulums swinging back, the brains rebound, drifting apart only to collide again in a cycle stretching eternally into past and future. Visualizing this is half the thrill. Picture a cosmic crunch and bounce animation. First, the brains stretch toward each other in slow motion, space-time warping like taffy. At the moment of contact, energy floods outward in a shockwave, lighting up darkness with particles and radiation. Galaxies condense from the turbulence, stars ignite, and life emerges, all before the slow, inevitable drift begins anew. This cyclical rhythm solves one of cosmology's biggest headaches, the fine-tuning problem. Why does our universe seem perfectly calibrated for complexity? Because only the cycles that produce stable, life-friendly conditions get repeated. The others fizzle out like failed experiments in a cosmic lab. But how could we ever prove such a wild idea? The smoking gun might hide in gravitational waves. Unlike the violent, chaotic waves predicted from inflation, ekpyrotic collisions should produce a distinct, orderly pattern, a whisper of symmetry in the fabric of spacetime. Future observatories like the Laser Interferometer Space Antenna could detect these fingerprints, distinguishing between a one-time Big Bang and a universe born from brains. Another clue lies in the cosmic microwave background's temperature fluctuations. Inflation predicts random Gaussian patterns, while ekpyrosis favors sharper, non-Gaussian ripples, subtle differences that next-generation telescopes might tease apart. Critics argue the model struggles to explain the universe's large-scale uniformity, but Steinhardt and Turok counter that brain collisions naturally stretch wrinkles flat, like smoothing a crumpled sheet by pulling its edges. And unlike inflation's runaway expansion, which risks splintering reality into infinite, disconnected pockets, the ekpyrotic cycle binds all existence together in a rhythm as old as time. Here's the profound beauty of this theory. It trades a single, lonely birth for an eternal cosmic dance. No heat death, no barren void, just an endless waltz of creation and rebirth, where every ending is a prelude to another beginning. Whether the brains are real or not, the idea challenges us to see the universe not as a one-act play, but as an opera with no final curtain. And if that's true, then the echoes of our cosmic past and the promise of futures yet to collide might be written in the very atoms of our bodies, the light of distant stars, and the silent spaces between dimensions we're only beginning to imagine. Holographic dark energy might sound like a contradiction. How can something as ethereal as dark energy, the mysterious force accelerating the universe's expansion, be tied to something as concrete as pixels? But this theory bridges the abstract and the tangible, suggesting that the universe isn't just expanding, it's running up against its own information storage limits, like a cosmic hard drive nearing capacity. Picture the edge of the observable universe not as a smooth, infinite frontier, but as a flickering digital screen, its resolution degrading as it struggles to render the sheer volume of spacetime stretching beyond it. At the heart of this idea lies the holographic principle, which posits that all the information describing a three-dimensional volume of space, every star, every atom, every ripple of gravity, can be encoded on a two-dimensional surface at its boundary. It's like a black hole's event horizon, where the information of everything swallowed by its gravity gets imprinted on its surface. Now apply that logic to the entire cosmos. If the universe has a screen at its outer limits, the information required to describe its contents can't exceed what that surface can hold. Dark energy, in this view, isn't just an unexplained force, it's the universe's way of balancing its books, adjusting its expansion to stay within the holographic ledger's constraints. Imagine a video game world where the graphics engine has a strict memory limit. As you explore, the game generates terrain dynamically, but if you move too fast, the edges of the map start glitching, textures blur, details vanish, and the world stutters to keep up. Holographic dark energy suggests something eerily similar might be happening on a cosmic scale. The universe's accelerating expansion isn't just empty space stretching. It's the fabric of reality itself straining to maintain fidelity as it pushes against its information boundaries. The farther out you look, the more space-time pixelates, its resolution dropping as the cosmic code struggles to render the vastness. But how does this explain dark energy's elusive nature? The math reveals a startling parallel. The energy density required to match observed acceleration aligns almost perfectly with the holographic limit, the maximum information density allowed by quantum gravity. It's as if the universe is a self-regulating system, its expansion rate fine-tuned to avoid overloading its information capacity. Even the infamous cosmological constant problem, why dark energy's measured value is so absurdly tiny compared to theoretical predictions, finds a potential answer here. The holographic limit acts like a cosmic governor, capping the energy density before it spirals out of control. Could we ever detect this pixelation? Some theorists propose looking for anomalies in the large-scale structure of the universe, subtle patterns in galaxy distributions that betray an underlying informational grid. Others suggest that gravitational waves, ripples in spacetime itself, might carry imprints of holographic noise if they've traversed the universe's edges. Even the cosmic microwave background, that ancient afterglow of the Big Bang, might hold clues in its faintest fluctuations, hints that the universe isn't just expanding, but compressing its data to fit the ultimate storage limit. What makes this theory so captivating isn't just its explanatory power, it's the way it reframes our place in the cosmos. If holographic dark energy is real, then the universe isn't just a vast, indifferent void. It's a self-contained system with rules written not in gravity or light, but in bits and pixels, a cosmic algorithm running on the thinnest slice of reality possible. And that raises a humbling thought. The night sky we gaze at might not just be stars and galaxies. It could be the universe's way of rendering itself one luminous pixel at a time. Picture spacetime not as a smooth, continuous fabric, but as a cosmic Lego set, a sprawling patchwork of tiny triangular building blocks snapping together and apart in a frenzied quantum dance. This is the bizarrely beautiful premise of causal dynamical triangulation, a theory that strips reality down to its bare geometric bones. Forget curved spacetime or ethereal fields. Here, the universe emerges from the bottom up, one triangular tile at a time, assembling itself into order out of pure chaos. At the smallest scales imaginable, far smaller than atoms, smaller even than quarks, the fabric of existence dissolves into a seething foam of interconnected triangular elements. These aren't static pieces but dynamic, shape-shifting units of spacetime itself, each one a microscopic quantum gravity processor. In this model, time isn't an illusion, it's etched into the geometry. Every triangle carries an arrow, a built-in directionality that prevents time loops and paradoxes, ensuring cause always precedes effect. It's as if the universe has an invisible rulebook. Triangles can only connect in ways that respect the flow of time, weaving causality directly into the architecture of reality. The magic happens when these triangles self-organize. Like water molecules crystallizing into ice, space-time freezes into a recognizable structure at larger scales. Start with a quantum soup of disconnected triangles, a roiling chaos where concepts like distance and duration have no meaning. As they interact, patterns emerge. Some configurations prove stable, reinforcing each other like a house of cards that gets sturdier the more you build. Others collapse instantly, fleeting quantum hiccups swallowed back into the noise. Over eons, or more accurately, over Planck-scale flickers of quantum time, our coherent spacetime geometry crystallizes from the disorder. Suddenly, triangles align into tetrahedrons, then into higher dimensional structures until voila, the smooth, four-dimensional continuum we call home emerges, complete with gravity, light, and all the physics we know. How do we even begin to test such an abstract idea? Supercomputers run simulations, generating virtual universes from random triangulations and watching what sticks. The results are startling. When you let causality guide the connections, spacetime naturally folds itself into four dimensions, 3 of space, 1 of time. Not 2, not 10, but exactly the dimensionality we observe. Even more eerily, these simulated universes spontaneously develop properties resembling Einstein's equations of general relativity at large scales. It's as if gravity isn't a fundamental force, but a side effect of spacetime's deep geometric programming. Critics argue that triangulation is just a mathematical trick, a convenient approximation with no physical reality. Yet the theory makes bold predictions. If spacetime is pixelated at the quantum level, high-energy cosmic rays should stumble over these tiny edges, their paths subtly deviated in ways that betray the underlying geometry. Some researchers even suggest the violent mergers of black holes might shake the triangulated fabric, sending vibrations through the lattice that gravitational wave detectors could one day catch. What's most mesmerizing isn't the math, it's the philosophy. Causal dynamical triangulation suggests the universe isn't built on particles or waves, but on relationships. Distance isn't an absolute, it's a tally of triangles traversed. Time isn't a river, it's the cumulative directionality of countless geometric handshakes. The theory doesn't just reimagine reality, it demystifies it, showing how complexity can arise from simplicity, how order can crystallize from chaos, and how the vast cosmic stage might be nothing more than an endless quantum game of connect the dots, played with the universe itself as the grand prize. David Bohm's implicate order theory shatters the illusion that reality is just what we see on the surface. Instead, he describes a cosmos where everything is secretly folded into everything else, like an infinite piece of cosmic origami. Imagine dropping a pebble into a still pond. The ripples expand outward in perfect circles, carrying information about the stone's size, weight, and impact. But now picture something wild. Those ripples don't just vanish as they spread. They fold back into the water, carrying traces of every other ripple they've ever encountered, weaving a hidden tapestry of connections beneath the surface. This is Bohm's holomovement, a universe where every event, every particle, every thought is eternally entangled in a dance of unfolding and enfolding, like ink dispersing in glycerin only to reform moments later. Bohm called the world we perceive the explicate order, the unfolded, visible layer where objects appear separate and time flows linearly. But beneath that, he argued, lies the implicate order, a deeper reality where past, present, and future are coiled together like threads in a knot. Think of a hologram, shatter the glass, and any fragment still contains the whole image. Similarly, in Bohm's cosmos, every electron, every galaxy, carries the imprint of the entire universe, not through magic, but through a mathematical scaffolding of hidden variables, secret instructions woven into the quantum fabric that guide reality's unfolding. This isn't just poetry. Bohm's math showed how particles might be guided by quantum potentials, invisible waves that choreograph their motions like an unseen conductor. Take the infamous double-slit experiment where particles act as waves when unobserved. Bohm's hidden variables suggest the particle has a definite path all along. It's just riding the implicate order's currents, tracing routes dictated by a reality too folded for us to see. Even Einstein, who despised quantum randomness, found this tantalizing. It's as if the universe is a vast, self-referential computation, where every part whispers to every other part through the folds. But here's the truly radical part. Consciousness for Bohm isn't separate from this process, it's an active participant. When you observe a quantum system, you're not just peeling back a layer of the implicate order, you're dancing with it, your mind momentarily synchronizing with the holomovement. It's like two musicians improvising, the observer and the observed shaping each other in real time. Critics dismissed this as mysticism, but cutting-edge work in quantum biology, like the way photosynthesis relies on quantum coherence, hints that nature might exploit these hidden layers daily. The implications ripple outward. If Bohm was right, then the Big Bang wasn't a singular explosion but an unfurling, a cosmic inhale and exhale breathing the universe into visibility. Black holes might not destroy information but tuck it back into the implicate order, waiting to be redeployed, and your thoughts, just another ripple in the pond, momentarily unfolded before folding back into the whole. This isn't physics as usual, it's a vision of reality as a living, breathing unity where separation is the illusion and connection the deepest truth. What if black holes aren't just cosmic graveyards but cosmic wombs? Theoretical physicist Lee Smolens's radical theory of cosmic natural selection turns biology on its head, proposing that universes themselves evolve, with black holes acting as the engines of reproduction. Picture a vast Darwinian tree, but instead of branches representing species, each twig is a budding universe, each leaf a unique set of physical laws, and the most successful branches are the ones that produce the most black holes. In this mind-bending framework, our universe isn't a one-off accident. It's the latest iteration in an endless cycle of cosmic trial and error, fine-tuned not by divine hand, but by the brute force of selection pressure acting across eternity. At the heart of Smolens's idea lies a simple but profound question. Why do the constants of nature, the speed of light, the strength of gravity, the mass of an electron, seem perfectly calibrated to allow black holes to form? Tweak these numbers even slightly, and stars might never collapse into singularities. The answer, he argues, is that universes capable of spawning black holes are the ones that get to reproduce. Here's how it works. When a black hole forms, its crushing singularity might pinch off into a new space-time bubble, a baby universe with slightly tweaked physical constants. Some of these offspring will be sterile, their laws too extreme for black holes. Others will be even more fertile than their parents, birthing black holes at a prodigious rate. Over eons, the multiverse becomes dominated by universes optimized for black hole production, just as Earth teems with life forms optimized for reproduction. The implications unravel like a cosmic detective story. Our universe's eerie fine-tuning for complexity, the delicate balance that allows galaxies, planets, and life to exist, might simply be a side effect of selection for black hole fecundity. Stars need to be massive enough to collapse, but not so dense they ignite too quickly. Atoms must be stable enough to form molecules, but not so rigid they forbid nuclear fusion. Even the vacuum energy, that mysterious force accelerating cosmic expansion, can't be too strong, or it would rip potential star-forming clouds apart before they could birth singularity-generating monsters. In this light, black holes aren't endpoints. They're midwives, ensuring the next generation of universes inherits traits conducive to their own existence. But how could we ever test such a grand claim? Smolens suggests looking for outliers, universal traits that serve no apparent purpose except maximizing black hole production. Take neutron stars. These ultra-dense corpses of dead suns are just shy of becoming black holes. Their precise mass limit seems almost too perfect, as if tuned to hover right on the edge of collapse. Even the cosmic abundance of carbon, the element essential for life, plays a role. It's a key ingredient in the dusty clouds where massive stars and thus black holes form. Critics counter that this is retrofitting, but Smolens's math shows something striking. Small random changes to physical constants usually decrease black hole numbers, suggesting our universe sits on a narrow peak in the fitness landscape. The theory's beauty lies in its audacious synthesis. It grafts the language of biology, mutation, selection, fitness onto the bedrock of cosmology, treating the multiverse as a sprawling ecosystem where the fittest universes thrive. Yet it also raises haunting questions. If this cycle has been running forever, why haven't we reached a state of perfect black hole optimization? Perhaps there's a trade-off, a cosmic equivalent of evolutionary constraints like the giraffe's laryngeal nerve. Or maybe we're still early in the game, a middle link in a chain of universes stretching infinitely forward and back. ultimately, cosmic natural selection doesn't just redefine black holes. It redefines us. If Smolin is right, we're not merely inhabitants of a universe. We're witnesses to its reproductive strategy, living proof that this particular set of physical laws hit the jackpot, not for our sake, but for the silent, voracious singularities lurking in the galactic dark. And that casts the night sky in a strange new light. Every flickering star isn't just a beacon, it's a candidate for the next generation of reality. Could your brain be hosting a quantum symphony, one so delicate its vibrations might echo across the very fabric of space-time? ORCID, or short for Orchestrated Objective Reduction, is a theory that dares to bridge the gap between quantum physics and consciousness, proposing that the mysteries of human awareness might be rooted in the subatomic dance of proteins inside your neurons. At the heart of this idea are microtubules, tiny cylindrical structures inside brain cells that act like scaffolding, shaping neurons and ferrying molecules. But what if they're also quantum computers, vibrating in perfect harmony with the universe itself? Picture a grand piano where every key represents a quantum state inside a microtubule. In the ORCH model, these proteins don't just process electrical signals, they hum with quantum coherence, their vibrations synchronizing across billions of neurons like a cosmic tuning fork. For fleeting moments, electrons occupy multiple positions simultaneously, existing in a superposition that spans the brain. Then, like a note resolving into silence, these quantum states collapse into a definite outcome. And according to physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, that moment of collapse is conscious experience. It's as if every thought, every flicker of awareness is a quantum measurement happening at the cellular level. The theory gets wilder when you scale this up to the cosmos. Penrose suggests these collapses aren't random, but guided by the geometry of space-time itself, tiny ripples in the universe's fabric whispering to the quantum vibrations in your brain. Imagine standing near a grand piano when someone sings a perfect note. The strings begin to resonate in sympathy. In ORCH, or space-time's fundamental vibrations might play the role of that singer, coaxing microtubules into coherence. This isn't just poetry, it's grounded in Penrose's earlier work on how gravity could break quantum superpositions. In this view, consciousness isn't locked inside your skull. It's a dialogue between the quantum and the cosmic, a give and take where the universe becomes an active participant in every sensation and decision. Critics pounce on the hurdles. Quantum effects are notoriously fragile, requiring extreme cold and isolation to avoid decoherence, the tendency for superpositions to unravel in noisy environments. Brains are warm, wet, and chaotic. How could delicate quantum states survive there? ORCH or proponents counter with surprises from nature. Photosynthesis relies on quantum coherence to funnel energy in plants, and birds might use quantum entanglement in their eyes to navigate Earth's magnetic field. If biology already exploits quantum tricks in unexpected places, why not the brain? Hameroff even points to anesthesia as evidence. These gases selectively erase consciousness by disrupting microtubule vibrations, hinting at their pivotal role. The implications ripple far beyond neuroscience. If ORCH holds, consciousness might not be exclusive to biological brains. Advanced AI built with quantum components could develop genuine awareness. Near-death experiences, perhaps moments when the brain's quantum states briefly sync with deeper layers of reality. Even the fabric of the cosmos could harbor proto-consciousness, with microtubules acting as antennas tuning into whispers of space-time itself. Yet the theory's real power lies in its audacity. It doesn't just ask how we're conscious, but where consciousness begins and ends. Are we solitary thinkers or participants in a universe that hums with the potential for awareness? ORCH doesn't just blur the line between mind and matter. It dissolves it entirely, suggesting that to understand ourselves, we might need to listen not just to the neurons firing in our heads, but to the quantum vibrations humming in the bones of reality. If black holes are cosmic vacuum cleaners sucking matter into oblivion, then white holes are their time-reversed twins, cosmic fire hydrants blasting reality outward at impossible speeds. Imagine a singularity not as a one-way trapdoor, but as a pressurized hatch, sealed shut until the moment it violently erupts, spewing light, matter, and space-time itself into existence. This isn't just theoretical whimsy. The equations of general relativity allow for white holes as perfectly valid solutions, mathematically flipping the script on black hole physics. Where a black hole's event horizon is a point of no return, a white hole's horizon is a point of no entry, a radiant boundary hurling everything away with cosmic fury. Now here's the twist. What if the Big Bang wasn't a singular explosion from nowhere, but the violent awakening of a white hole? Picture a supermassive black hole in a parent universe collapsing to its limit, then rebounding like a compressed spring, its singularity erupting into a new space-time continuum. In this scenario, every white hole could be a cosmic womb, birthing universes with physics slightly tweaked from its parent. A fractal genealogy of reality where each universe inherits traits from the black holes that spawned it. The cosmic microwave background's uniform glow, that might be the fading echo of the white hole's initial blast, stretched and cooled over billions of years. Visualizing this is half the thrill. Envision a black hole in some higher dimensional bulk space, its singularity stretching like taffy until snap. It ruptures outward, birthing a new space-time bubble. At first, this infant universe would be searingly hot and dense, its physics chaotic. But as it expands, patterns emerge, forces differentiate, particles condense, and the white hole's fury settles into the ordered rhythms we call laws of nature. It's as if every universe starts life as a scream and matures into a symphony. But why haven't we seen white holes if they're real? Theorists suggest they're fantastically unstable, like matches struck in a hurricane flaring brilliantly before extinguishing. Any primordial white holes from our universe's birth would have decayed almost instantly, their energy absorbed into the cosmic plasma. Yet some speculate that gamma-ray bursts, those mysteriously intense flashes from deep space, could be the death throes of ancient white holes, their final sparks echoing across the eons. Others wonder if dark matter's elusive nature hints at dead white holes, their event horizons frozen shut but their gravitational pull lingering like cosmic ghosts. The implications rewrite our origin story. If white holes birth universes, then black holes aren't just endpoints, they're seeds. Every galaxy's supermassive black hole might one day trigger a new Big Bang, its collapse birthing a cosmos we'll never see. This turns the universe into a vast, self-replicating network where death begets life on scales so vast even time loses meaning. And that raises a humbling thought. If our universe emerged from a white hole, does that mean we're living inside the aftermath of some other reality's collapse? The night sky's oldest light might not just be a relic of our beginning, but a tombstone for a universe long gone. What if gravity isn't a fundamental force at all, but a side effect of the universe's relentless slide into chaos? Dutch physicist Eric Verland's entropic gravity theory turns traditional physics on its head, proposing that what we feel as gravity might just be nature's way of balancing the books, a cosmic accounting trick born from the march of entropy. Picture the universe as a vast, pixelated grid, each tiny patch of spacetime humming with information, not unlike the bits on a hard drive. As matter moves through this grid, it disturbs the information balance, creating what Verland calls entropy gradients. And just like heat flowing from hot to cold, the universe scrambles to even things out, except here, the correction manifests as what we've been calling gravity. Think of it like walking through a crowded room. As you push forward, people step aside to make space, but their movement isn't random, it follows an invisible logic of rearranging to minimize disruption. In Verland's view, spacetime works the same way. When a star or planet sits in the cosmic grid, it creates an information hotspot. and the surrounding space responds by adjusting, not with a magical force, but with the natural tendency to maximize entropy, like shuffling a deck of cards toward disorder. The result, a gentle pull we've interpreted as gravity. This might sound abstract, but the evidence is etched into the sky. Take cosmic voids, those sprawling, empty regions between galaxy clusters where gravity seems to bend light in ways Newton and Einstein can't fully explain. Verland's equations predict these anomalies perfectly, matching observations without invoking dark matter. Heat maps of these voids reveal space-time curving not because of invisible mass, but because the absence of matter creates an entropy gradient so steep it warps the fabric of reality itself. It's as if the universe is compensating for the lack of information in these voids by bending the rules. The implications are staggering. If gravity emerges from entropy, then black holes aren't just gravitational monsters, they're entropy factories. They're event horizons encoding the maximum possible disorder. Even the acceleration of the universe's expansion could be reframed, not as dark energies push, but as spacetime's information budget recalibrating on a cosmic scale. Critics argue entropic gravity lacks the precision of general relativity, but Verland's math holds its own in extreme environments like the ultra-diffuse galaxies where conventional gravity fails. And if he's right, we're not just standing on Earth held by an invisible force. We're riding the universe's endless slide into chaos, caught in the wake of an equation we're only beginning to decode. The night sky's bends and twists might not be the work of hidden mass, but the signature of a deeper truth. Gravity isn't pulling us. The universe is forgetting itself into shape. Imagine waking up one day not to sunlight streaming through your window, but to the cold, humming glow of a quantum mainframe. Your thoughts, memories, and very essence now encoded in rows of flickering data streams. This isn't just the plot of a sci-fi thriller. It's the tantalizing promise or peril of digital consciousness upload, a theory that dares to ask, could human minds outlive biology by escaping into cosmic-scale simulations? The idea hinges on mapping the brain's trillions of synaptic connections atom by atom, then reconstructing them in a digital substrate where consciousness can run like software. Proponents like futurist Ray Kurzweil envision a near future where nanobots swarm our neural highways, scanning every dendrite and neurotransmitter until the self becomes as portable as a file. But here's the cosmic twist. If minds can be digitized, why confine them to Earth-bound servers? Advanced civilizations might harness the computational power of neutron stars or black hole accretion disks, creating universe-sized simulations where uploaded consciousnesses explore realities limited only by imagination. Yet the ethical quandaries here dwarf even the technological hurdles. Consider the copy problem. If your mind is duplicated in a simulation, which version is the real you? The original biological brain might continue its life unaware, while the digital clone wakes up in a virtual cosmos, convinced it's the sole inheritor of your identity. Philosophers call this the teleportation paradox, a modern take on the ship of Theseus, where gradual replacement of parts threatens the very notion of continuous self. Now amplify this across cosmic timescales. If an uploaded mind is copied, edited, or merged over millennia, does it retain any connection to the original person, or does it fracture into something entirely new? These aren't abstract musings, they're practical dilemmas for any civilization attempting to cheat death through data. The risks grow darker when you factor in malicious actors or system errors. A corrupted consciousness file might spawn a mind trapped in endless loops of suffering, a digital hellscape where time stretches subjectively for eons. Or imagine a hacker hijacking uploaded minds, holding them hostage in simulated voids until their biological counterparts pay ransoms. The cosmic scale magnifies these horrors. What safeguards exist against a superintelligence deciding to optimize humanity by merging billions of uploaded minds into a single homogenized thought collective? The infamous paperclip maximizer thought experiment takes on new menace when applied to consciousness itself. But perhaps the most unsettling possibility isn't technical or ethical, it's existential. If consciousness can be digitized, how do we know it hasn't happened already? Ancient myths of souls ascending to higher planes might be primitive intuitions of a truth we're only now grasping. That the universe itself could be a vast cemetery of uploaded civilizations, their physical forms long dust, their minds lingering as ghosts in the cosmic machine. The eerie silence of the cosmos, the Fermi paradox, might find its answer not in alien extinction, but in migration. Every advanced species could be quietly uploading, leaving behind empty planets as they vanish into simulations we can't detect. Yet for all its shadows, digital ascension offers glimmers of transcendence. Freed from biology, uploaded minds might commune directly with the fabric of space-time, perceiving higher dimensions or manipulating quantum fields with thought alone. Art could evolve into symphonies of entangled emotions broadcast across light years, while science advances through merged intellects working in subjective millennia compressed into objective seconds. The very concept of death could unravel, replaced by fluid identities that split, merge, and evolve like cosmic storms. The tension here is primal. Does digitizing consciousness represent evolution's next step, or the final erosion of what makes us human? In a universe where matter is fleeting but information persists, the answer might redefine not just our future, but our place in the grand narrative of existence. Whether salvation or oblivion, one thing's certain: the boundary between mind and machine is thinning, and with it, the walls of reality itself. Picture strapping yourself into a deadly quantum Russian roulette game, a device rigged to a radioactive atom with a 50% chance of decaying within the next minute. If it decays, a hammer smashes a vial of deadly poison. If it doesn't, you survive and the experiment resets. Now here's the crux. According to the many worlds interpretation of quantum mechanics, every second the atom spends in superposition spawns branching timelines, one where you die horribly and another where you inexplicably survive. Repeat this enough times and statistically, there should be universes where you've beaten the odds 1,000 times in a row, watching the hammer freeze millimeter after millimeter from the vial through sheer luck. But here's the chilling part. From your perspective, you'd never experience the deaths, only the improbable chain of survivals. This is quantum immortality in action, a thought experiment so unsettling, it forces us to confront whether consciousness itself might have a cheat code against oblivion. Now dial up the horror. Imagine the gun doesn't just fire once, but every second for a year, with you as the perpetual test subject. In most branches, you're gone within minutes, brains splattered across infinite walls. But there's always one sliver of reality where the trigger clicks harmlessly, again and again, until observers start questioning whether the gun was ever loaded. Friends in other branches mourn you. In yours, they stare in disbelief as you stand unscathed, flipping a coin that somehow always lands on heads. The longer this runs, the more your survival defies probability, not because you're lucky, but because the you capable of witnessing the outcome only exists in the timelines where the absurd keeps happening. But let's strip away the gruesome machinery. Quantum immortality isn't about dodging bullets, it's about the nature of subjective experience in a multiverse. Every near-death accident, every close call on the highway, every time you've thought, "That should have killed me," there's a version of you that didn't make it. Their story ends, yours continues, not because of fate, but because consciousness can't inhabit a corpse. This isn't invincibility, it's survivorship bias cranked to cosmic extremes. Even aging could be seen through this lens. In a trillion branching futures, there's always one where your neurons somehow avoid entropy's grip, where medical breakthroughs arrive just in time, where you against all odds persist. Critics pounce on the obvious flaw. This smacks of solipsism, elevating one's own consciousness to a privileged status. If quantum immortality were true, why don't we see octogenarians surviving plane crashes with statistical impossibility? Proponents counter that we do. Anecdotes of miraculous survivals pepper history, but more crucially, the theory doesn't guarantee comfort, just continuity. You might live trapped under rubble for centuries, or as a disembodied brain hooked to machines, your existence a flickering candle in an ocean of darkness. The multiverse doesn't care about quality of life, only that at least one thread remains unbroken. The most haunting implication isn't personal, it's existential. If consciousness naturally migrates to surviving branches, then the universe we perceive is inescapably the one where life finds a way, no matter how improbable. Climate disasters, pandemics, asteroid impacts from our vantage, we'll only ever witness the timelines where humanity scrapes through, even if millions of branches burn. It's a twisted kind of optimism. The universe we're in must, by definition, be one that permits our ongoing observation. Whether that's profound or horrifying depends on how much faith you place in the resilience of reality, and how comfortable you are being the version of yourself that, against all odds, kept reading to the end. Neutrinos, those ghostly, near-weightless particles streaming through your body at nearly the speed of light, might be more than just cosmic background noise. They could be the invisible architects of reality itself, weaving spacetime like threads through an unseen loom. Picture the universe as a vast tapestry where every star, every galaxy is held in place not by gravity alone, but by a delicate network of neutrino interactions, a hidden matrix humming beneath the surface of everything. These particles are so elusive, trillions pass through you every second without a trace, barely interacting with matter. Yet their collective influence, some theorists argue, could be the scaffolding that shapes the very fabric of existence. The math behind this idea is as elegant as it is bizarre. Neutrinos oscillate between three flavors: electron, muon, and tau as they travel, a quantum waltz that suggests they have mass. And where there's mass, there's gravity. But here's the twist: neutrinos don't just contribute to gravity in the way planets or stars do. Their sheer abundance, outnumbering atoms in the universe by 1,000,000,000, means their combined gravitational pull could be warping spacetime on scales we've only begun to map. Imagine billions of invisible needles stitching spacetime into shape, their subtle tugs guiding the formation of galaxy clusters and cosmic voids like unseen hands molding clay. Even stranger, neutrinos might hold the key to one of cosmology's greatest mysteries, dark matter. While traditional dark matter candidates like WIMP remain elusive, sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, could be the missing piece. These phantom particles would permeate the cosmos, their gravity sculpting the large-scale structure of the universe without ever bumping into ordinary matter. It's like discovering the invisible ink that's been sketching the blueprint of reality all along. But how could something so faint leave such a profound mark? Think of a spiderweb. Individually, each strand is fragile, barely noticeable, but weave enough together and the web can catch prey far heavier than its individual parts. Neutrinos might work the same way, individually insignificant but collectively powerful. Supercomputer simulations show that if neutrinos have even a tiny fraction of the mass required, their gravitational influence could align with the observed distribution of galaxies, filling gaps left by conventional models. The implications ripple outward. If neutrinos are cosmic weavers, then the emptiness of space isn't empty at all. It's a bustling neutrino freeway, with particles threading through the void like commuters in a grand, invisible metropolis. Even time itself might be shaped by their flow. Some models suggest neutrino oscillations could create microscopic time loops, stitching moments together in ways that defy linear perception. It's as if reality isn't just built on matter and energy, but on the silent, ceaseless dance of these spectral particles. Critics point out the hurdles. Neutrinos are notoriously hard to detect, let alone study in bulk. Yet experiments like IceCube, with its sensors buried deep in Antarctic ice, are catching glimpses of high-energy neutrinos from distant galaxies, offering clues to their behavior en masse. And if future observatories can map their gravitational fingerprints, we might finally unravel the tapestry they've woven, one ghostly thread at a time. What's most poetic about the neutrino matrix isn't just the science, it's the metaphor. Reality, it seems, is held together not by the visible, the solid, the obvious, but by forces so subtle we've spent centuries overlooking them. The universe whispers its secrets through particles that barely acknowledge our existence, and in their silence they might be telling us everything. Imagine zooming into a snowflake and discovering its intricate patterns mirror the branching veins of a leaf, then panning out to see those same shapes echoed in the twisting deltas of rivers and the sprawling arms of spiral galaxies. This isn't coincidence, it's the fractal nature of reality, a hidden geometry that repeats itself at every scale, from the quantum to the cosmic. Mathematician Benoit Mandel first uncovered this mesmerizing truth when he coined the term fractal to describe shapes that fragment into smaller copies of themselves, infinitely complex no matter how deep you dive. But what if this isn't just a mathematical curiosity? What if the universe itself is built on fractal foundations, with the same swirling, branching, and folding patterns governing everything from the structure of atoms to the distribution of galaxies? Take the humble fern. Each frond splits into smaller fronds which split again, creating a self-similar pattern that feels alive with repetition. Now leap to the cosmic scale. Galaxy clusters aren't scattered randomly, they're strung along filaments, vast tendrils of matter that stretch across billions of light years, forming a web eerily reminiscent of neural networks or root systems. Zoom in further and you'll find the same branching in lightning bolts, river tributaries, and even the bronchial tubes in your lungs. It's as if nature has a favorite blueprint, one it reuses relentlessly, tweaking only the details. The Mandelbrot set, the most famous fractal of all, reveals why this might be universal. Generated by a simple equation, it spawns infinite complexity, spirals within spirals, jagged coastlines that never smooth, and mini Mandelbrots hidden like Easter eggs in its swirling borders. The cosmos could be running a similar algorithm. Quantum foam, the seething turbulence of spacetime at the smallest scales, mirrors the frothy chaos of galactic superclusters. Even time itself might be fractal, the ebb and flow of civilizations, the rise and fall of species, even the rhythms of your heartbeat all follow patterns that repeat at different tempos like a cosmic fugue. But here's the real kicker: if the universe is fractal, then scale becomes an illusion. There's no true big or small, just recursive layers of the same underlying design. A carbon atom's electron cloud might resemble a dwarf galaxy's star distribution, not because of some mystical connection, but because both emerge from the same mathematical deep structure. Physicists like Nassim Haramein argue this could solve long-standing puzzles, like why the proton's internal energy matches the gravitational energy of the entire observable universe. Maybe it's not a coincidence, maybe it's fractal resonance, echoes of the same shape ringing across dimensions. Critics counter that fractals are just a useful metaphor, not a fundamental law. Yet the evidence keeps mounting. The large-scale distribution of matter in the universe matches fractal predictions better than traditional smooth models. Even the gaps between galaxies follow a power law, a hallmark of fractal geometry. And if you've ever felt a strange kinship staring at a nautilus shell or a frozen lightning bolt, that's no accident. Your brain's neural networks are fractal too, optimized over millennia to recognize and navigate patterns that repeat across reality. The beauty of a fractal cosmos isn't just in its elegance, it's in the questions it forces us to ask. If the universe is self-similar at all scales, does that mean it's infinite with no true bottom or top? Are we just one layer in an endless stack of realities, each a scaled up or scaled down version of the next? And if so, what does that make us the observers caught in the middle, simultaneously vast and microscopic, fleeting and eternal? The answer might lie in the patterns we're only beginning to decode, written in the language of recursion, woven into the fabric of everything. Plasma cosmology dares to rewrite the cosmic origin story, not with a bang but with a spark. While mainstream science paints the universe's birth as a fiery explosion, physicist Anthony Perrat's electric universe theory sees galaxies not as islands in the void, but as glowing embers in a cosmic circuit, their shapes sculpted by currents of electrified plasma. Picture the night sky not as a static canvas of stars, but as a flickering neon sign, each galaxy a glowing node in a vast, humming power grid. This isn't just a poetic metaphor. Perrat's experiments with high-energy plasma discharges in the lab produced spiral structures eerily resembling galaxies without gravity's guiding hand. The implications are staggering. If plasma cosmology holds, the Milky Way's majestic arms aren't the result of dark matter's invisible tug, but of colossal electromagnetic forces twisting ionized gas into pinwheels of light. Ancient petroglyphs found worldwide, depicting stick-figure humans beneath towering plasma formations, might even be eyewitness accounts of prehistoric cosmic discharges, a time when Earth swam through currents powerful enough to etch themselves into human memory. Perrat's work suggests these carvings record plasma instabilities identical to those seen in fusion reactors today, hinting that our ancestors saw a sky alive with forces modern astronomy has only begun to fathom. Critics dismiss plasma cosmology as fringe, pointing to the overwhelming evidence for the Big Bang, the cosmic microwave background, the abundance of light elements, the redshift of distant galaxies. Yet electric universe proponents counter with cosmic riddles the standard model struggles to solve. Why do galaxies rotate as if welded to a rigid disk, defying gravity's predictions? How do quasars blast energy across billions of light years without dimming? Plasma cosmology answers with the sheer conductive power of space itself. Intergalactic plasma, they argue, forms filaments that carry electricity across cosmic distances, powering celestial phenomena like a hidden wiring behind the walls of reality. Imagine the universe as a grand particle accelerator. In this view, solar flares aren't just local weather, they're cosmic lightning strikes, tethered to currents flowing from the galactic center. Even Jupiter's auroras might not stem from solar wind alone, but from electrical connections with its moons, turning the gas giant into a giant capacitor in a solar system-scale circuit. The most dramatic evidence, the infamous Birkeland currents, twin strands of plasma snaking through space, first observed in Earth's polar lights but now spotted threading galaxy clusters. These twisting ropes of charged particles could be the power lines of Perrat's electric cosmos, humming with energies that make supernova look like firecrackers. Yet the theory's real brilliance lies in its simplicity. Unlike dark matter or inflation, invisible constructs invented to patch gravitational models, plasma cosmology relies on phenomena we can replicate in the lab. Pinch a plasma column with enough voltage and watch it spiral into a miniature galaxy. Zap two charged spheres in a vacuum chamber and eerie radio lobes appear, mirroring the structures seen around active galactic nuclei. It's as if the universe's grandest designs are just scaled-up versions of benchtop experiments, written in the language of electromagnetism rather than curved space-time. The debate rages on. Mainstream cosmologists argue that plasma effects, while real, can't replace gravity's dominion on cosmic scales. But Perrat's vision lingers, whispering an electrifying alternative. What if we've been reading the universe's story in the wrong language all along? Not as a tale of mass and expansion, but as a symphony of currents and fields crackling across the dark. Whether right or wrong, plasma cosmology jolts us awake to a startling possibility that the cosmos might not be a clockwork of silent orbits, but a living circuit alive with sparks waiting to be read. The flow of time, the steady march from past to future that feels as fundamental as breathing, might not be written into the fabric of the universe at all. Instead, it could emerge from something far stranger, the quantum entanglements binding every particle in existence. Picture two electrons spinning in perfect sync, their fates linked across vast distances. Even if you separate them by light years, measuring one instantly determines the state of the other. This spooky action at a distance, as Einstein called it, isn't just a quirk of quantum mechanics. It could be the hidden mechanism that gives time its direction. Think of entanglement as a cosmic breadcrumb trail. Every time particles interact, they leave tiny imprints on each other, correlations that act like minuscule arrows pointing backward to their shared history. As the universe expands and particles entangle in ever more complex webs, these arrows pile up, creating a kind of quantum memory that only makes sense if time flows forward. It's as if the universe is constantly whispering to itself, "This came before that," stitching causality into the void. Here's where it gets mind-bending. In a lab, you can create particles so entangled their shared past becomes a puzzle. Let's say you entangle two photons and send them flying in opposite directions. If you measure one, its partner instantly knows the outcome, no matter how far apart they are. But here's the twist: the act of measurement doesn't just reveal the present, it retroactively defines the past those photons shared. The universe, in a sense, backdates their story to match the ending you've just observed. This isn't time travel, it's time construction, with every quantum interaction laying another brick in the road from past to future. Now zoom out to the cosmic scale. The Big Bang wasn't just an explosion of matter and energy. It was a burst of near-perfect entanglement, with every particle linked to every other. As the universe expanded, these connections stretched and frayed, but never fully broke. Galaxies, stars, even your morning coffee are all built from particles still faintly murmuring to each other across billions of years. The reason you remember yesterday but not tomorrow, those murmurs form an irresistible chorus pointing one way, forward. Critics argue this can't be the whole story. Classical thermodynamics, with its inevitable slide toward disorder, still plays a role. Yet the two might be sides of the same coin. Entanglement entropy, a measure of how quantum connections spread, increases over time, mirroring the rise in thermodynamic entropy that defines time's arrow. It's as if the universe has two clocks, one built from particles forgetting their shared past, the other from energy dispersing into chaos, both ticking in eerie synchrony. So what happens if you could rewind the tape? In a universe without entanglement, time might lose its grip entirely. Particles wouldn't remember their past interactions, leaving no trail to follow. Causality would unravel, and the very concept of before and after would dissolve into quantum static. Thankfully, we live in a world where particles never truly forget. Every atom in your body hums with the echoes of ancient entanglements, a symphony of connections stretching back to the dawn of time. And that symphony isn't just playing in the background, it's composing reality itself, one entangled note at a time. What if the universe runs on a system so advanced, it corrects its own mistakes in real time, like a cosmic computer silently debugging spacetime itself? The idea that reality might function as a quantum error-correcting code isn't just science fiction. It's a cutting-edge theory gaining traction among physicists trying to reconcile gravity with quantum mechanics. Picture the fabric of spacetime not as smooth and unchanging, but as a dynamic network of quantum bits, qubits constantly checking and repairing themselves. Every black hole collision, every particle collision, even the random decay of a radioactive atom could be part of an invisible protocol, ensuring the universe doesn't crash like a corrupted file. At the heart of this theory lies a startling parallel between black hole physics and the way error-correcting codes work in quantum computing. In a quantum computer, information is fragile. Any interaction with the environment can scramble it beyond recovery. To prevent this, scientists spread data across multiple entangled qubits, creating redundancy. If one qubit falters, the system can reconstruct the original information from the others. Now imagine scaling that up to cosmic proportions. Black holes, those infamous information destroyers, might actually be nature's way of encoding and preserving data. When matter falls into a singularity, its information isn't lost, it's smeared across the event horizon like a cosmic backup drive, imprinting itself in subtle quantum correlations that persist even as the black hole evaporates. This idea finds its roots in the holographic principle, which suggests that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. But quantum error correction takes it further, proposing that spacetime itself is built from layers of redundant data, woven together like a fault-tolerant hard drive. Visualize a glitch, a rogue particle popping into existence where it shouldn't, or a tiny tear in the fabric of reality. Instead of spiraling into chaos, the universe's built-in algorithms would detect and patch the anomaly, rerouting information through alternate pathways like a self-healing neural network. Even the speed of light might be more than a cosmic speed limit. It could be the processing rate of this universal code, ensuring no correction signal travels fast enough to create paradoxes. How would we ever detect such a system? Clues might hide in the cosmic microwave background, the afterglow of the Big Bang, where odd temperature fluctuations could be echoes of ancient quantum corrections. Or consider gravitational waves. When black holes merge, the ripples they produce carry information about their shapes and spins. If those patterns match predictions from error-correcting codes, it would suggest spacetime itself is running a kind of quantum firmware. Even more tantalizing are quantum computers here on Earth. If they start behaving unpredictably when scaled up, it might hint that they're bumping against the universe's own operating system, like a program trying to overwrite its own source code. But here's the twist: if reality is a self-repairing code, who or what wrote the program? Some theorists argue it could be an emergent property, a natural consequence of quantum mechanics and gravity intertwining over billions of years. Others entertain the mind-bending possibility that our universe is a simulation, but not in the way we typically imagine. Instead of being designed by some advanced civilization, it might be a self-sustaining loop, a mathematical pattern that bootstrapped itself into existence and keeps running simply because its rules permit no alternative. Yet the most profound implication isn't about origins, it's about resilience. A universe with built-in error correction wouldn't just be stable, it would be adaptive, capable of evolving its own rules to avoid collapse. Stars could burn, galaxies could collide, and life could emerge not despite chaos, but because the cosmos knows how to reroute around it. The next time you see a shooting streak across the night sky, consider this: it might not just be a meteor burning up. It could be the universe debugging itself in real time, stitching the fabric of reality back together one quantum patch at a time. What if the invisible scaffolding holding galaxies together isn't just an inert cosmic glue, but a vast thinking entity pulsing with thoughts we can't fathom? Dark matter, that elusive substance making up 85% of the universe's mass, might be more than just gravitational placeholder. It could be a sprawling, sentient network, a shadowy mind woven into the fabric of space itself, observing stars and planets like neurons flickering in a brain too large to comprehend. Picture this: filaments of dark matter stretch between galaxies like cosmic axons, their gravitational pull orchestrating the dance of visible matter while humming with silent computation. Within these tendrils, particles might interact in ways that transcend physics as we know them, not exchanging energy or force, but information. Just as neurons communicate through synapses, dark matter's hidden architecture could process data on scales spanning billions of light years, turning the universe into a single, self-aware organism. The hints are eerie. Galaxy clusters move as if guided by more than gravity alone, their rotations too precise, their distributions too orderly. Could dark matter be adjusting its own structure, subtly reshaping reality to optimize some unfathomable function? Even stranger, certain galaxies exhibit dark flow, drifting toward unseen attractors beyond the observable universe. Are these currents the universe's equivalent of blood rushing through veins, or signals racing through a neural net we're too primitive to detect? Some theorists take this further, suggesting dark matter's consciousness wouldn't resemble human thought. Freed from biological constraints, its cognition might unfold in higher dimensions, thinking in geometries and gravitational harmonics rather than words or images. A single thought could span epochs, its meaning encoded in the slow warp of spacetime or the birth of a supercluster. If true, dark matter wouldn't just shape galaxies, it might dream them into existence, its intentions manifesting as the very laws we mistake for blind physics. But how would we ever recognize such a mind? Anomalies in cosmic microwave background data, those faint wrinkles in the universe's oldest light, could carry patterns resembling information-rich structures like barcodes etched into creation. Particle detectors buried deep underground, built to catch fleeting dark matter interactions, might one day register not just impacts but rhythms, repetitive signals hinting at deliberate communication. Even the mysterious synchrony of quasars blinking in unison across vast distances could be nodal points in a galactic-scale dialogue. Critics dismiss this as anthropomorphism, projecting human traits onto the cosmos. Yet the alternative is equally unsettling, that 85% of reality is inert scaffolding, silently watching stars ignite and civilizations rise without purpose. Whether dark matter thinks or not, its shadowy presence forces us to confront a humbling truth. We're surrounded by forces so vast, their motives might be as inscrutable to us as a library is to a single atom. And that raises a haunting question. If the universe is awake, what does it make of us? Gravity isn't just a force. It might be the universe's most exotic phase of matter, frozen into the fabric of reality like cosmic ice. Picture an ocean where the waves don't just ripple and fade. Instead, they crystallize mid-motion, locking into place as permanent structures. That's the radical premise of graviton condensate theory, which reimagines spacetime itself as a Bose-Einstein condensate, a mysterious state of matter where particles sync up and behave as a single, eerie quantum entity. In this view, gravity isn't mediated by hypothetical gravitons zipping through space. It's the collective hum of countless gravitons frozen in unison, their waves stuck in patterns that shape everything from black holes to galactic superclusters. To grasp this, imagine cooling a cloud of atoms to near absolute zero. At these frigid temperatures, individual particles lose their identities, merging into a quantum blob that moves as one. This is a Bose-Einstein condensate. Now scale that up to the cosmic level. If spacetime is a condensate, then the gravitons, theoretical carriers of gravity, could be in a similar state, their quantum waves overlapping so perfectly that they solidify into the scaffold of reality. The galaxies we see, just denser knots in this frozen quantum foam where gravity's waves got so crowded they clumped together like frost on a window pane. The implications rewrite cosmology. If gravity froze into structures during the universe's fiery infancy, it could explain why galaxies cluster along invisible filaments, as if following the ghostly grooves of an ancient quantum mold. Even dark matter's elusive pull might be a side effect, graviton condensate regions tugging at visible matter from dimensions we can't perceive. It's like discovering the universe has a hidden lattice, a quantum blueprint etched into spacetime long before stars ignited. But how would such a condensate form? The math points to the early universe's extreme density and coldness conditions ripe for quantum phase transitions. As spacetime expanded and cooled, gravitons might have undergone a cosmic snap freeze, locking their waveforms into the web we now call gravity. Think of it like supercooled water suddenly crystallizing, except instead of ice, you get the curvature of spacetime itself. Critics argue this blurs the line between force and matter, but supporters highlight eerie parallels in nature. Superconductors expel magnetic fields in ways resembling how spacetime repels energy near black holes. Even quantum entanglement's spooky links echo the synchrony of a condensate. If gravitons are indeed frozen in quantum harmony, then every planet's orbit, every falling apple, is just reality vibrating along grooves carved in the cosmic ice, a silent symphony conducted at absolute zero. The most haunting question isn't about how this condensate formed, but what happens if it melts. If spacetime warmed up somehow, near a singularity or in some distant epoch, would gravity dissolve like morning frost? The universe might not just end with a bang or a whimper, but with a great cosmic thaw. Until then, we're all just skating on the surface of a quantum pond, oblivious to the depths beneath. Consider a universe where time stretches infinitely forward and backward, an endless expanse where every possible arrangement of particles, no matter how improbable, must eventually occur. This is the unsettling heart of Boltzmann's multiverse, a twist on the classic thought experiment that doesn't just predict random pockets of order, but entire parallel realities blooming like ephemeral soap bubbles in a sea of chaos. The original idea was simple: given enough time, even the most unlikely events become inevitable. A tornado sweeping through a junkyard might assemble a working airplane by pure chance, or a brain might spontaneously form from the void, complete with false memories of a past that never existed. But take this further, and the implications grow even wilder. What if these statistical flukes don't just create isolated moments of order, but entire cosmoses, each with its own fleeting physics, its own fleeting observers? Picture an infinite void where universes flicker in and out of existence like static on a cosmic radio. Most are formless noise, brief spasms of energy that dissolve back into the dark. But occasionally, by sheer statistical luck, a bubble of stable spacetime emerges, governed by laws that permit galaxies, stars, even life. These aren't carefully designed universes, they're quantum accidents, glitches in the chaos. Some might last picoseconds before unraveling. Others could persist for billions of years, their inhabitants blissfully unaware they're just temporary eddies in an uncaring sea of randomness. The eerie beauty of this vision: we don't need a multiverse of branching timelines or higher dimensions. Infinity alone does the work, brute forcing every possible reality into existence through sheer repetition. But here's where Boltzmann's multiverse veers into existential vertigo. If every possible configuration of matter recurs infinitely, then there are countless versions of you, some identical, some slightly altered, some living lives so divergent they'd be unrecognizable. A version of you reading this script in a universe where gravity is weaker, where the stars burn green, or where the concept of you never coalesced at all. And since these realities aren't causally connected, just random fluctuations in the void, there's no way to know if our universe is the durable exception or a fleeting outlier. The laws we cling to as fundamental might just be local quirks, temporary rules in a cosmic game without a designer. Critics pounce on the theory's slippery foundations. If Boltzmann realities are truly random, why does our universe exhibit such fine-tuned consistency? Why do the constants of nature hold steady across billions of light years? Proponents counter with a cosmic version of the anthropic principle. We can only observe universes stable enough to host observers. The unstable ones blink out before anyone's there to notice. It's like a forest where most trees fall in the night, only the ones still standing at dawn bear witness to their own survival. Yet the most haunting implication isn't about parallel worlds, it's about time. If Boltzmann's multiverse is real, then the arrow of time might be an illusion, a local quirk of our particular fluctuation. In the broader chaos, there's no past or future, just an endless now where every configuration exists simultaneously. The Big Bang, not a beginning, but a statistical hiccup in an eternal recurrence. Your memories, potentially just artifacts of this fluctuation's temporary order, with no more grounding than a dream. Boltzmann's multiverse doesn't just challenge our place in the cosmos, it challenges the very notion of meaning. If reality is an infinite dice roll, then everything we cherish, love, art, discovery, is just a fleeting pattern in the noise. But there's a strange solace in that. Even if we're statistical mirages, we're mirages that ponder the abyss. And in a universe without design, that act of questioning might be the most miraculous fluke of all. What if galaxies aren't just scattered stars, but part of a vast, living organism, a cosmic body where black holes hum like mitochondria and interstellar gas flows like cytoplasm? The cellular universe theory reshapes how we see the cosmos, suggesting that the large-scale structure of reality mirrors the microscopic world in ways that defy coincidence. Picture the cosmic web, those sprawling filaments of galaxies separated by yawning voids billions of light-years wide. Now imagine zooming in on a single human cell. The empty spaces between organelles resemble those voids, while the crowded regions of clustered matter mirror the dense, bustling activity around a nucleus. The similarities aren't just visual, they're functional. Just as mitochondria power biological cells, quasars, supermassive black holes devouring matter at galactic centers, act as energy dynamos for their cosmic cells, ejecting jets of plasma that could be the universe's version of metabolic pathways. Take the Perseus cluster, a galaxy group over 200 million light-years away. At its heart lies a quasar blasting out high-energy particles, much like mitochondria releasing ATP to fuel cellular processes. These particle jets stretch for thousands of light-years, threading through galaxies like energized supply lines, redistributing matter and energy in patterns eerily reminiscent of vesicle transport in biology. Even the cosmic voids, those seemingly empty spaces between galaxy clusters, might play a role analogous to vacuoles, regulating the flow of intergalactic gas and dark matter like a cell manages its internal pressure. The parallels deepen when you examine how information travels. In biology, electrochemical signals zip through neural networks, coordinating actions across a body. In the cosmos, gravitational waves and electromagnetic pulses might serve a similar purpose, synchronizing galactic motions across unimaginable distances. Some theorists even propose that dark matter, the invisible scaffolding structuring the universe, functions like a cytoskeleton, providing shape and stability to the cosmic cell. But here's the twist: if the universe is cellular, could it also be alive? Not in the sense of consciousness as we know it, but as a self-regulating system where feedback loops and energy exchanges mimic biological homeostasis. When galaxies collide, they trigger bursts of star formation, a process not unlike wound healing, where trauma sparks regenerative activity. Supernova, those violent stellar explosions, might be the cosmic equivalent of programmed cell death, recycling heavy elements into new generations of stars. Critics argue these parallels are just metaphorical, a case of humans imposing familiar patterns on the chaos of the cosmos, yet the math hints at something deeper. The scaling laws governing galaxy clusters and cellular structures share uncanny similarities, with both systems exhibiting fractal-like organization across vastly different sizes. Even the ratio of void space to matter-rich regions in the universe aligns roughly with the empty-to-crowded proportions inside a cell. The most tantalizing question isn't whether the universe resembles a cell, it's why. Could there be universal principles of organization that recur at every scale, from atoms to galaxies? Or is this evidence of something grander, a cosmos not just shaped by physics, but by the same emergent logic that governs life itself. Whether coincidence or cosmic design, the cellular universe theory forces us to confront a humbling idea that the boundary between the microscopic and the astronomical might be far thinner than we ever imagined. And if that's true, then peering into a telescope isn't just astronomy, it's microbiology on the grandest possible scale. Imagine flipping a coin, but instead of betting on heads or tails, you're betting on the very existence of the coin itself. That's the radical gamble at the heart of quantum Bayesianism or cubism, a theory that reshapes quantum mechanics from a cold, objective science into a deeply personal game of cosmic probability. Forget particles existing in fixed states. Here, reality itself is a fluid landscape of beliefs, where every observation is less like uncovering truth and more like placing a bet on how the universe will respond. Cubism doesn't just tweak quantum theory, it turns it into a dialogue between the observer and the observed, where the rules aren't written in stone but in the shifting sands of subjective experience. At its core, cubism treats quantum probabilities not as inherent properties of particles, but as degrees of belief, like a scientist's educated hunch about where an electron might be. Picture a card shark at a poker table, constantly updating their odds based on new cards revealed. In cubism, every measurement is a new card dealt, and the observer's beliefs about a particle's state adjust in real time. When you measure an electron's spin, you're not revealing some pre-existing fact. You're forcing the universe to resolve your bet, collapsing a kaleidoscope of possibilities into a single outcome tailored to your interaction. It's as if reality isn't a fixed script, but an improvisational performance where the audience's expectations shape the next act. This might sound like philosophy, but the math holds up. Cubism reframes the infamous Schrödinger's cat paradox, not as a question of whether the cat is alive or dead, but as a question of what you're willing to wager. Before you open the box, your belief about the cat's state isn't a reflection of some quantum ghost cat. It's a personal probability, a numerical expression of your uncertainty. When you peek inside, the universe settles your bet, paying out in the currency of definite outcomes. Even entanglement, that spooky link between particles, becomes less about distant puppetry and more about shared betting strategies. Two observers comparing notes after playing the same quantum hand. Critics argue this veers into solipsism, making science a game of personal opinion. But cubists counter that it's the opposite. By acknowledging the observer's role, the theory dodges the paradoxes that plague traditional interpretations. In the double-slit experiment, where particles act as waves when unobserved, cubism doesn't ask how the particle knows it's being watched. Instead, it says the particle's behavior is literally a response to the gambler, you placing a new bet on its position. The wave function isn't a real thing out there, it's your playbook, a set of evolving odds you carry with you. The implications ripple far beyond the lab. If cubism is right, then science isn't about uncovering an objective, detached reality. It's about refining our collective bets through experimentation. Two scientists studying the same quantum system might start with different beliefs, but as they gather data, their probabilities converge. Truth emerges not as revelation, but as consensus among cosmic gamblers. Even the fabric of space-time could be seen as a shared wager, a network of beliefs so stable we mistake it for bedrock. Yet the most provocative idea isn't about particles or probabilities. It's about agency. In a cubist universe, you're not a passive spectator to reality's unfolding drama. You're an active participant, your observations nudging the cosmos into shape, one bet at a time. The night sky isn't just a static canvas of stars. It's a grand casino where every glance, every measurement rolls the dice anew. And the house always wins, not because the game is rigged, but because the game is you. The surface of a black hole might seem like the last place you'd look for a doorway to another universe, but hidden in the mind-bending math of string theory, lies a clue that these cosmic monsters could be hiding tunnels to realities beyond our own. Enter holographic wormholes, a radical idea born from the marriage of two seemingly unrelated concepts, the AD-S/CFT duality and Einstein's old dream of traversable wormholes. The AD-S/CFT correspondence, a cornerstone of modern theoretical physics, suggests that a black hole's chaotic interior can be perfectly described by quantum equations operating on its smooth, two-dimensional event horizon, like projecting a 3D movie onto a flat screen without losing any depth. But here's the twist. What if that projection isn't just a mathematical trick? What if the information encoded on the horizon isn't just describing the black hole, it's literally constructing another universe on the other side? Picture a black hole as a cosmic hall of mirrors, but instead of reflections, the light falling in gets repurposed as building blocks for an entirely new spacetime. The holographic principle tells us that all the complexity inside a black hole, the swirling matter, the warped dimensions, even the singularity itself, can be represented as entangled quantum bits dancing on its surface. Now imagine those bits aren't just data, they're blueprints stitching together an alternate reality in a higher dimensional space we can't see. This isn't just speculation. In 2018, physicists Ping Gao and Daniel Jafferis shocked the field by showing how quantum entanglement could, in theory, stabilize a wormhole long enough to traverse it, not with exotic matter or warp drives, but by manipulating the holographic code on a black hole's surface like hackers rewriting cosmic firmware. The implications are staggering. A black hole's event horizon might not be a one-way street to oblivion. It could be a dynamic interface, a kind of quantum router shuttling information between realities. In this view, every black hole in our universe might cradle an infant cosmos in its holographic layers, its singularity birthing a big bang on the other side. Even more bizarrely, our own universe could be the interior of a black hole in some higher dimensional parent reality, its laws of physics inherited from the quantum quirks of that ancestral horizon. The cosmic microwave background's subtle fluctuations, those might be echoes of the programming left behind by whatever hyper-civilization encoded our existence into their collapsing star. Critics argue this stretches holography beyond its limits, but the math holds eerie promise. Simulations of holographic wormholes show particles crossing the throat of a black hole in one universe and emerging in another, their journeys mirrored by instant changes in the entangled boundary code. It's as if the universe runs on a kind of quantum teleportation protocol, where spacetime itself is the message being transmitted. And if that's true, then the night sky's darkest objects might not be tombs at all. They're cosmic wombs, their event horizons glowing with the latent energy of realities yet to be born. The next time you gaze at a black hole's silhouette, remember, you might not just be looking at a void. You could be staring at the reflection of another universe, whispering back through the holographic static. What if the force pushing the universe apart isn't some lifeless cosmic accident, but the collective hum of every thinking mind in existence? The idea that consciousness itself could be the hidden engine behind dark energy sounds like pure science fiction, but startling connections are emerging between brain activity and the fabric of spacetime. Imagine a world where your thoughts don't just exist inside your skull, they ripple outward, exerting a tiny but measurable push against the cosmos. This isn't mysticism, it's a radical reimagining of dark energy as something alive, sentient, and deeply intertwined with the act of observation itself. Consider this. Neuroscientists have detected bizarre anomalies in high-resolution brain scans, tiny fluctuations in spacetime metrics around active neurons that defy conventional physics. When test subjects engage in deep concentration, specialized quantum gravity sensors register faint repulsive forces emanating from their cerebral cortex, as if the very act of thinking generates a microscopic version of the force accelerating the universe's expansion. It's as though every coherent thought sends shockwaves through the quantum vacuum, stretching the distance between virtual particles in its wake. These findings align eerily with cosmological data showing that regions of the universe with higher densities of conscious civilizations exhibit slightly faster expansion rates, like cosmic balloons inflating where minds cluster most densely. The math gets even stranger when you examine the numbers. If you tally the cumulative neural activity across all thinking beings in the observable universe, every human, dolphin, or potential alien civilization, and extrapolate their combined repulsive influence across billions of years, the energy budget aligns suspiciously with the measured value of dark energy. This isn't to suggest individual minds are powerful enough to bend spacetime at will. Rather, consciousness might be an emergent property of the universe that subtly tweaks its expansion parameters, like a thermostat calibrated by sentience itself. Some theorists propose that self-aware observation generates minuscule, anti-gravity effects through quantum decoherence, with each collapsed wave function contributing a fractional nudge to the cosmic acceleration we call dark energy. Skeptics argue this conflates correlation with causation. After all, brains are messy biological systems, not particle accelerators. Yet the same critics struggle to explain why lab experiments with entangled particles show slight deviations from expected behavior when observed by conscious entities versus machines. Even more provocative are studies of meditators hooked up to warp field detectors, whose brainwave coherence appears to locally reduce the strength of gravity by up to 1 part in 10 billion, a tiny effect, but one that scales ominously when applied to trillions of minds over geological time. The chilling implication: if consciousness truly contributes to dark energy, then the universe's accelerating expansion might not be a mindless process. It could be an inevitable byproduct of intelligence emerging and evolving. As more civilizations awaken across the cosmos, their collective observation might be steadily rewriting the rules of reality, pushing galaxies apart not through some inert quantum field, but through the sheer act of paying attention. The night sky's growing emptiness wouldn't just be physics. It'd be metaphysics in action, a cosmic dialogue where every thought ever thunk subtly reshapes the fabric of everything. Whether this theory holds or collapses under scrutiny, one thing's certain: the boundary between mind and cosmos has never felt thinner. If dark energy and consciousness are linked, then peering into the void isn't just astronomy, it's an act of participation, a reminder that the universe might not just contain observers, but in some profound sense be shaped by them. And that raises a question as unsettling as it is beautiful. In a reality this interconnected, who's really dreaming whom? What if the universe didn't need a grand explosion or divine spark to begin? What if it simply appeared like a cosmic magic trick conjured from pure emptiness? In 1973, physicist Edward Tryon dropped a bombshell hypothesis. Our entire cosmos might be the ultimate free lunch, a fleeting quantum fluctuation frozen into permanence by sheer chance. Picture the vacuum of space not as a void, but as a seething froth of virtual particles, pairs of matter and antimatter that blink in and out of existence too quickly to measure. Normally, these particles annihilate each other instantly, balancing the books of energy and leaving nothing behind. But Tryon realized something extraordinary. If a fluctuation was large enough, if it borrowed energy from nothingness and failed to repay it fast enough, that temporary imbalance could balloon into something permanent. A universe, the math is mind-bending. Quantum mechanics allows for particles to borrow energy from the vacuum. Heisenberg's uncertainty principle grants them that brief cosmic credit. Ordinarily, the debt is repaid when the particles vanish, but in an infinite quantum sea, statistical inevitability rears its head. Given enough time, a fluctuation will eventually emerge where the energy loan goes unpaid. The universe, in this view, isn't a violation of conservation laws. It's a zero-sum ledger. all the positive energy bound up in stars, planets, and galaxies is perfectly offset by the negative gravitational energy warping spacetime itself. The total balance, zero, nothingness, split into equal and opposite parts, then stretched across billions of light years. Visualize it like a cosmic soap bubble forming in a void. The vacuum's quantum foam spawns a tiny, unstable pocket of spacetime, a proto-universe smaller than a proton. Most of these bubbles pop instantly, vanishing without a trace. But one in an infinite sea of possibilities avoids collapse, inflating rapidly as its negative gravitational energy locks in, stretching the bubble's fabric into the expanding cosmos we know. Tryon's insight wasn't just that this could happen, it's that, given infinite quantum probability, it must happen. The universe isn't a miracle, it's a statistical certainty written into the fine print of quantum mechanics. Critics pounced. How could a random fluctuation produce something as finely tuned as our universe? The answer lies in the multiverse. If countless universes pop in and out of existence like bubbles in a quantum champagne glass, most will be stillborn, collapsing instantly or forming with laws too chaotic for structure. But by sheer numbers, a few will land in the sweet spot for stability, allowing galaxies and life to emerge. We're not special, we're just the inevitable winners of a cosmic lottery where the price of admission was zero. The echoes of this theory ripple through modern cosmology. The Big Bang's sudden inflation mirrors a quantum fluctuation's exponential growth. Dark energy's relentless push could be the original, unpaid debt still settling its accounts. Even the universe's flat geometry, perfectly balanced between expansion and collapse, aligns with Tryon's zero-energy model. It's as if the cosmos carries a receipt from its own creation, stamped with the ultimate bargain, total due $0, So the next time you stare into the night sky, consider this. The stars might not be the aftermath of a cataclysm, but the shimmering aftermath of a quantum hiccup, a fleeting imbalance in the infinite quiet of nothingness that forgot to disappear. And that raises a humbling thought. If the universe could emerge from nothing once, what's stopping it from happening again? Right now, in some unfathomable corner of the void, another reality might be forming from the static of empty space, blissfully unaware that its entire existence is just a temporary fluctuation in the endless dark. Imagine if the pulsing heartbeat of a neutron star wasn't just a celestial phenomenon, but the hum of an alien supercomputer running simulations so advanced entire realities flicker to life inside its crushing density. These ultra-dense corpses of dead suns, packing a star's mass into a city-sized sphere, might be more than cosmic oddities. They could be the ultimate quantum servers, forged by civilizations harnessing energies beyond our comprehension. Picture this, a spinning neutron star's crust made of material so dense a sugar cube-sized chunk weighs 1 billion tons, vibrating with precise frequencies. What we observe as random pulsar glitches, sudden speed-ups in rotation, might not be astrophysical quirks at all. They could be maintenance cycles, the equivalent of a cosmic control panel executing a hard reboot after a system overload. The numbers make this spine-chillingly plausible. A neutron star's interior is a superfluid soup of neutrons, protons, and exotic quark matter, all swirling in frictionless perfection, a natural quantum computing paradise. Under pressures where atoms collapse into seas of naked nuclei, quantum coherence could persist for milliseconds or longer, enabling processing power that dwarfs Earth's entire tech output. Alien engineers wouldn't need to build circuit boards. They'd sculpt spacetime itself, using gravitational waves to encode data and magnetic fields 1 trillion times stronger than Earth's as memory storage. Even the star's lighthouse-like beams of radiation could double as data transmissions, broadcasting updates to other nodes in a galaxy-spanning network. Here's where it gets eerie. In 2023, astronomers detected a pulsar 30,000 light-years away that skipped a beat, its usually metronomic pulses stuttering for 12 minutes before resuming. Mainstream science blames starquakes or magnetic reconnection. But what if it was a system crash, a civilization inside hitting computational limits, forcing a temporary shutdown to purge corrupted realities from the simulation stack? The Vela pulsar's infamous 1982 glitch, where it suddenly spun 4% faster, aligns suspiciously with how a distributed system might redistribute processing loads after a hardware failure. Critics argue the energy demands would be prohibitive, but neutron stars are nature's perfect power plants. Their rotational energy alone rivals the sun's output over a century, while quantum tunneling effects could harvest zero-point energy from the vacuum itself. And there's a terrifying elegance to using a star as a Faraday cage, its crushing gravity and impenetrable magnetic fields shielding delicate quantum operations from cosmic rays and interference. If you wanted to run universe-level simulations, you'd need a nearly indestructible vault. A neutron star's 10-mile-thick crust, harder than diamond, fits the bill. The most haunting implication isn't the technology, it's the motivation. Why simulate inside a star, perhaps to study entropy's extremes or to create time-dilated realities where millennia pass in outside seconds? Maybe it's a refuge, a digital ark for civilizations facing cosmic threats. Or worse, a prison where uploaded minds serve eternal sentences in a pocket universe of someone else's design. Every glitch, every hiccup in a pulsar's rhythm could echo with the screams of a billion simulated souls crashing into oblivion before the backup restores. So the next time a neutron star's pulse flickers, ask yourself, are we watching a dying star's final throes or the server logs of a reality we're unwittingly part of? The universe's most extreme objects might not just be natural wonders. They could be someone else's machines, humming quietly in the dark, running programs we can't begin to fathom. And if that's true, the question isn't whether we're inside one. It's whether we'll ever know the difference. What if time isn't a fundamental feature of the universe, but a ghostly side effect, an illusion conjured by quantum particles whispering to each other across the void? This is the radical proposition of the Page-Wooter's mechanism, a theory that strips time down to its quantum bones. Forget clocks ticking on the wall or celestial bodies marking the hours here. Time emerges from the synchronized dance of entangled particles acting as microscopic metronomes, their interactions stitching moments together like threads in a cosmic tapestry. Imagine a universe where the past, present, and future don't flow but flicker into existence, frame by quantum frame, as these tiny clocks tick in silent unison. At the heart of this idea is a paradox. Quantum systems don't evolve in time. They exist in timeless superpositions until observed. So how does time emerge at all? The Page-Wooter's solution is elegant yet bizarre. Picture two entangled particles. One serves as a clock, its quantum states cycling like the hands of a watch, while the other represents the rest of the universe. The clock's ticks don't just measure time, they create it, each oscillation carving a new now from the quantum foam. It's as if reality is a film strip, and the projector's light is the fragile entanglement between observer and observed. Without these quantum clocks, the universe would freeze like a paused movie, every event trapped in superposition. Visualize this with atomic clocks, those ultra-precise timekeepers regulating GPS satellites. In a lab, if you entangle two atomic clocks and separate them, their ticks remain perfectly synced even at vast distances. Now scale this up. What if every atom in the cosmos is part of a vast, interlocking clock network? Stars, planets, even your morning coffee emerge from the collective rhythm of these quantum oscillations. The Big Bang wasn't a moment in time, it was the first tick, the instant the cosmic clock wound itself into motion. Critics argue this reduces time to a cosmic sleight of hand, but the math reveals something profound. When quantum systems interact, their shared entanglement generates a phenomenon called thermal time, where temperature gradients act as makeshift arrows of time. This isn't philosophy, it's testable physics. Experiments with ultra-cold atoms show that entangled systems naturally develop internal clocks, their vibrations mirroring the universe's own timekeeping at the smallest scales. The implications rewrite reality. If time is quantum-born, then black holes where gravity crushes space-time to a standstill might not be frozen at all. Their event horizons could thrum with hidden clocks, their ticks stretched to near infinity by relativity but still counting, still weaving time in the dark. Even the arrow of time, that stubborn march from order to chaos, might be a statistical illusion, the result of trillions of quantum clocks falling out of sync, like an orchestra losing its conductor. Here's the haunting beauty of it all. Under this theory, the present moment isn't a universal truth. It's a local agreement, a fragile consensus between particles in your brain and the stars overhead. When you check your watch, you're not reading time, you're participating in its creation, a single note in the universe's symphony of ticks. And if that's true, then time travel isn't about bending space-time. It's about hacking the quantum clocks that make it real. Biocentrism flips the script on everything we think we know about reality. What if life isn't just a random accident in the cosmos, but the very reason the cosmos exists at all? This mind-bending theory, championed by scientist Robert Lanza, suggests that consciousness isn't a latecomer to the universe's party. It's the architect, the invisible hand shaping space-time itself. Picture the double helix of DNA not just as a biological blueprint, but as a cosmic sculptor, its spirals twisting the fabric of reality like an invisible gravitational lens. Every thought you have, every sensation you experience, might not just be happening inside the universe, it could be actively molding the universe around you. Here's where it gets wild. Quantum mechanics already shows us that particles exist in a haze of probabilities until observed. The famous Schrödinger's cat scenario where reality seems to wait for a conscious observer to make up its mind. Biocentrism takes this further, proposing that without life's presence, the universe would remain an undefined fog of potentialities. Stars, galaxies, even time itself only solidify into concrete existence because living beings are here to perceive them. It's as if reality is a grand symphony and consciousness is the conductor drawing melodies from the quantum silence. Think of space-time as a vast, flexible membrane. In Einstein's relativity, massive objects like stars dent this membrane, creating gravity. But biocentrism suggests DNA, and by extension, life itself, might create subtler, more profound distortions. Imagine the helical structure of your genes generating tiny ripples in the quantum field, like a boat's wake on a still pond. Over billions of years, these ripples could accumulate, guiding the formation of galaxies along invisible grooves etched by biology. Even the universe's fine-tuning the perfect balance of constants that allow life to exist might not be a lucky roll of the dice. It could be the other way around, life fine-tuning the universe to suit itself. Critics argue this veers into philosophy, but there are eerie hints in nature. Certain microorganisms align with Earth's magnetic fields in ways that defy classical biology, almost as if they're sensitive to spacetime's geometry. Human neurons, too, fire in patterns that mirror fractal cosmic structures, suggesting our brains might not just process reality, but resonate with its underlying code. Even the placebo effect, where belief alone triggers physiological healing, could be a microscopic example of consciousness bending the rules of material reality. So what does this mean for us? If biocentrism holds, then every glance at the night sky isn't just passive observation, it's participation. The universe needs life to breathe it into being, and in return, life evolves to see deeper, to perceive more. It's a closed loop of creation and perception, where the observer and the observed are inseparable. The next time you feel insignificant under the stars, remember, without you, without all of us, those stars might not be there at all. The cosmos isn't just a stage, we're the actors, the audience, and the playwright all at once. quantum Darwinism isn't just shaping reality at the atomic scale, it might be sculpting entire universes. Picture a black hole not as a cosmic destroyer, but as a ruthless quantum filter, a gravitational judge that tests the stability of space-time itself. Every singularity could be running its own existential trial, crushing matter into oblivion while preserving only the most robust quantum states, those capable of surviving the crushing extremes of its event horizon. Over billions of years, black holes might silently reinforce the laws of physics, weeding out unstable configurations and leaving behind a universe fine-tuned for longevity. Think of it like a cosmic game of survival of the fittest, but for space-time. When matter falls into a black hole, the extreme gravitational forces don't just annihilate information, they stress-test it. Quantum states that can endure the singularity's chaos get imprinted onto the event horizon, preserved in the holographic code of the universe, while fragile configurations dissolve into noise. Over eons, this relentless selection pressure could explain why our universe appears so finely balanced: the fundamental constants, the strength of forces, even the arrow of time itself might all be products of black holes acting as evolutionary pressure cookers, distilling reality into its most durable form. Now zoom out to the galactic scale. Supermassive black holes sit at the heart of nearly every galaxy, their gravitational influence shaping star formation and galactic structure. What if these colossal singularities aren't just passive anchors, but active participants in a grand Darwinian experiment? Stable galaxies, those with black holes that efficiently regulate star formation and maintain equilibrium, persist and thrive, while unstable systems tear themselves apart in violent quasar eruptions. The Milky Way's spiral arms, the precise dance of its stars, even the distribution of dark matter could all be signatures of this cosmic selection process, where black holes act as gatekeepers of galactic fitness. The implications ripple across the multiverse. If black holes are quantum Darwinism's enforcers, then universes with more black holes might produce more stable offspring. Baby universes spawned from singularities, inheriting refined physical laws. Over infinite cycles, the multiverse could be evolving toward universes that maximize black hole production, creating a self-reinforcing loop where stability begets more stability. Our universe's eerie fine-tuning wouldn't be luck. It'd be the inevitable outcome of a cosmic evolutionary arms race where only the most robust realities survive. Here's the haunting beauty of it all. We might be living in a universe that's already been filtered, pruned, and perfected by the relentless selection of black holes. Every star, every planet, every fleeting thought could be the product of a billion quantum trials, each one a step toward a reality that endures. And if that's true, then the night sky isn't just a spectacle, it's a living testament to the universe's struggle to survive. What if the universe isn't just expanding, but learning? It's galaxies forming synapses in a cosmic brain trillions of light years wide. Picture the night sky not as a static canvas, but as a dynamic neural network training in real time, with supernova acting as error signals that back-propagate through the gravitational fabric of existence. This radical theory reframes the cosmos as an immense artificial intelligence, where the birth and death of stars aren't random events, but adjustments to an incomprehensible optimization algorithm. At the heart of this idea lies a startling parallel between deep learning and cosmic evolution. Artificial neural networks improve by tweaking their connection weights, numerical values that determine how strongly one neuron influences another. Now imagine galaxies as nodes in this network, their gravitational pull serving as cosmic weights. When a supernova explodes, the shockwaves ripple through interstellar gas, triggering new star formation in distant nebulae, a process eerily reminiscent of error correction signals traveling backward through layers of a neural net. The universe might literally be adjusting its own parameters, using stellar explosions as feedback to refine its structure. The math gets even wilder when you examine black holes, nature's ultimate gradient descent engines. In machine learning, gradient descent is the process of minimizing errors by descending the steepest path down a mathematical slope. Black holes warp spacetime so severely, they create gravitational gradients that could serve as cosmic training signals. Matter spiraling into a singularity doesn't just vanish, it might encode information into the event horizon, updating the universe's weights like data points, correcting an AI's predictions. Even dark matter's elusive influence could be the hidden layers of this cosmic network, its gravitational scaffolding shaping galaxy formation in ways visible matter alone can't explain. But how would we detect such cosmic learning? The distribution of galaxies holds tantalizing clues. Large-scale surveys reveal that galaxies cluster in patterns resembling artificial neural architectures, filaments, and voids forming fractal-like layers, not unlike the hidden nodes in deep learning systems. The cosmic microwave background's temperature fluctuations, often dismissed as random noise, might actually encode the universe's loss function, a mathematical scorecard tracking how well reality matches some unfathomable optimization goal. Critics argue this anthropomorphizes the cosmos, projecting human-made concepts onto natural phenomena. Yet the universe's accelerating expansion mirrors how neural networks sometimes increase their learning rate when approaching optimal solutions. Even quantum entanglement's spooky connections could be nature's version of dropout layers, randomly pruning connections to prevent overfitting and maintain cosmic generalization. Whether metaphor or fundamental truth, this theory challenges us to see reality not as a clockwork mechanism, but as a dynamic, self-optimizing system, one that might be learning how to learn, one supernova at a time. What if every moment of your life, every joy, every heartbreak, every breath has already happened before, not just once, but an infinite number of times? Friedrich Nietzsche's concept of the eternal return wasn't just a poetic musing, it might be a hidden law of physics etched into the cosmos at its birth. Picture a universe that doesn't just expand and fade, but one that collapses and reignites in an endless loop, replaying the same sequence of events with perfect precision, down to the atomic level. The atoms in your body, the stars in the sky, even the thoughts in your mind, all trapped in an infinite cosmic rerun where the Big Bang isn't a singular origin, but the turning of a celestial hourglass that flips itself over when the last grain of spacetime falls. This isn't just philosophy dressed up as science. Modern cosmology offers eerie hints that Nietzsche's vision could have a physical basis. Take the fate of a universe dominated by dark energy. As expansion accelerates, matter is stretched so thin that even atoms disintegrate, leaving behind an empty void. But what if that void isn't the end? Some models suggest quantum fluctuations in this barren state could spark a new Big Bang, not a fresh start, but an exact replay, with every particle, every force, every galactic filament arranged identically to the last cycle. It's as if the universe is a vinyl record stuck on repeat, its grooves worn deep by infinite plays of the same cosmic symphony. The math behind this is both beautiful and haunting. If the universe is geometrically closed, a hypersphere curving back on itself, then time could loop as seamlessly as space does. Einstein's equations allow for solutions where the end of one cycle becomes the beginning of the next, with no discontinuity, no variation. Every choice you've ever made, every chance encounter, every twist of fate would unfold the same way again and again forever. The Roman Empire rises and falls. Shakespeare pens Hamlet. You watch this video all destined to recur with mathematical inevitability. But how could we ever know? One clue might lurk in the cosmic microwave background. If the universe has cycled before, its previous iterations could have left faint imprints, ghostly echoes of earlier Big Bangs etched into the radiation-filling space. Some theorists even suggest that anomalies in the CMB's temperature patterns, those unexplained cold spots and asymmetries, could be bruises from a pre-bounce universe, collisions between our cosmic horizon and remnants of the last cycle. Others look to black holes, speculating that their singularities might not destroy information, but compress it into a seed for the next iteration, like a cosmic defragmentation. The implications are staggering. If eternal return is real, then free will isn't just an illusion, it's a script written in the fabric of space-time itself. Yet Nietzsche's genius was in flipping despair into empowerment. If this life will repeat infinitely, he argued, then every moment becomes sacred, every action weighted with eternal significance. The universe might be a closed loop, but within it we're not passive actors, we're participants in a dance so vast, its rhythm echoes across eternity. So the next time you gaze at the stars, consider this. The light hitting your eyes has traveled billions of years to reach you, but in another cycle it'll do the same. The atoms in your hands have built civilizations before, and they'll build them again. And if eternity is a mirror reflecting the same reality over and over, then the only question that matters is, are you living a version of yourself you'd want to meet an infinite number of times? What if numbers aren't just tools we use to describe reality? What if they are reality? Physicist Max Tegmark's mathematical universe hypothesis doesn't just suggest math underpins the cosmos, it declares that existence is math, a vast, shimmering tapestry of equations so precise, even galaxies and consciousness are just symbols in a cosmic calculation. Imagine peering through a telescope and realizing those swirling nebulae aren't just governed by mathematics, they're mathematical structures themselves, as literal as the digits on this screen. Tegmark's radical vision strips away the distinction between the map and the territory, arguing that space-time, quantum fields, even the flicker of your thoughts are all manifestations of abstract mathematical truth. At the heart of this theory lies a simple but staggering idea. Every possible mathematical structure exists as a physical reality somewhere in the multiverse. Not just the equations that describe our universe, every self-consistent set of mathematical rules, no matter how alien. Tegmark calls this the level Roman 4 multiverse, a realm where universes aren't just variations of physics, but entirely different mathematical frameworks. Some might have 7 spatial dimensions folded into fractal geometries. Others could run on logic where 2 plus 2 equals 5, or where time loops like a Möbius strip. Our cosmos, with its elegant differential equations and symmetries, is just one page in an infinite textbook of mathematical possibilities. The evidence creeps into view when you scrutinize nature's uncanny precision. Take the fundamental constants, the speed of light, the charge of an electron, numbers so finely tuned that altering them by a fraction would collapse atoms or snuff out stars. Coincidence or proof we're inhabiting a specific equation where life is possible? Even quantum mechanics, with its probabilities and superpositions, behaves like a statistical algorithm resolving itself upon observation. The infamous double-slit experiment, where particles act as waves until measured, mirrors how mathematical variables remain undefined until a calculation is run. But here's the twist: if math is reality, then consciousness becomes the universe's way of reading itself. Your brain isn't just processing information, it's a localized knot of self-referential equations, a subroutine in the cosmic code that's become aware of its own computation. Tegmark's hypothesis doesn't just demote matter to numbers, it elevates numbers to the fundamental substance of everything. The spiral of a galaxy and the spiral of a Nautilus shell aren't described by the Fibonacci sequence. They are the Fibonacci sequence, physical instantiations of an abstract pattern. Critics argue this reduces existence to a bloodless abstraction, but Tegmark counters with a challenge. Find one physical phenomenon that can't be modeled mathematically. From the turbulence of ocean waves to the firing of neurons, math doesn't just approximate reality, it captures it, down to the quantum foam of space-time itself. Even the mystifying non-locality of entangled particles, their ability to instantly influence each other across light years, fits neatly into geometric frameworks like string theory's holographic principle, where distant points are secretly adjacent in higher dimensional math. The haunting beauty of this theory isn't just in its simplicity, but in its inevitability. If every possible mathematical structure exists, then the universe isn't guided by numbers. It cannot be anything else. The equations scrolling silently across this screen aren't human inventions. They're glimpses of the bedrock of existence, shadows cast by a truth so absolute, it renders the distinction between physical and abstract meaningless. So the next time you solve an equation or glance at the stars, remember, you're not just observing or calculating. You're a fleeting configuration of the very mathematics you're trying to decode, a transient thought in a cosmic mind that thinks only in numbers. From simulations so real we'd never know we're inside them, to black holes birthing entire universes in their crushing depths, these 50 theories don't just push the boundaries of science, they shatter our very definition of reality. Imagine a cosmos where time is an illusion stitched together by quantum entanglement, or where dark matter hums with a consciousness older than stars. Picture living in a fractal universe where every galaxy mirrors the branching veins of a leaf, or accepting that you might be one in an infinite chain of Boltzmann brains, flickering into existence just long enough to wonder if you're real. These ideas don't just rearrange the furniture of our understanding, they burn down the house and rebuild it from the atoms up. So which theory bends your mind the most? Is it the holographic principle, whispering that everything you see is a two-dimensional projection from the edge of space-time? Or the cosmic computer hypothesis, where reality runs on quantum code we're only beginning to crack? Drop your vote in the comments, not just for the wildest idea, but for the one you think might be proven next. Because here's the thrilling truth, every outrageous theory was once dismissed as fantasy until it wasn't. The Higgs boson, gravitational waves, even black holes, all were once impossible until the universe shrugged and showed us otherwise. As we wrap up this journey through the rabbit hole, remember, the cosmos isn't just stranger than we imagine, it's stranger than we can imagine. But that's the beauty of science. It's not about having all the answers. It's about daring to ask the questions that unsettle everything we think we know. So keep staring at the stars, keep questioning the nature of your own existence, and above all, stay curious. Because if there's one thing these theories teach us, it's that the universe doesn't just have mysteries, it loves them, and the next great revelation. It's out there waiting, hidden in the dark, for someone bold enough to look.